learned. So you could either say you want to do solar system, large or small nebulae, and stuff like that. Or maybe you want astrophotography. The difference between the optics, this is designed more for observing. It has some color correction, chromatic correction. And this would be more for astrophotography. It has more correction for color. So I'm hoping that this would serve as a roadmap for people who are new and haven't bought a telescope. So this is the process I went through. And it's a good summary, I think, because you end up running all around over online and trying to find all this stuff. So I put it all together. And so this is some way forward. But you need to ask yourself these questions. If you get a grab and go, chances are you'll most likely use that more often because you can just grab it and take it out. So there are a lot of, I call them little technical details, just a lot of little tiny things. If you look at it all at once, it's overwhelming, but the bits and pieces aren't as overwhelming. So I'm just, every slide here and there, I'm going to insert a bit of technical notes as we move along, just so you know. And also, you should think about your budget. In this range, $500–600 range, you might want to look for a U-scope somewhere on Kijiji. But if you do that, you really have to know your stuff to make sure you're not getting ripped off. So you have to have quite a bit of knowledge to work in this area, but you can find some pretty good deals. Then there's a medium price budget. And I must say that this talk is somewhat biased towards me, so you can adjust the ranges, but this is from my research. So you can get a decent astrophotography free scope, like a good start. Decent tripods and mounts, but you have to be careful. You could also get ripped off with the drive systems and everything at that price range. You may not get something that's optimal. Okay, so I'm going to talk about that a bit. And the sky's the limit. Well, you better know your stuff, know what you want, otherwise it'll end up becoming a very expensive coat rack. So, but someone can buy that then on Kijiji. So you see a lot of coat racks out there. Also, something I learned when I first joined the RASC was one question not to ask. So how much did you spend on that rig? So I learned very quickly people don't like being asked that question. However, in order for you to get something out of this talk, I'm going to tell you how much I spent on my rig. Okay, so, yeah. So, and then you'll learn that why it's important to ask someone to use their equipment before touching it, handling it, because it's quite an expense. It can be. Okay, so what were my criteria? I decided, actually it was funny because I remember when I looked through those old Tasco telescopes, and you see like a tiny little Saturn. I said, okay, I just want to see the biggest possible Saturn. So I wanted something planetary. So I decided something within the solar system. So for moons, sun, and so forth. So I decided to go planetary. Something that was astrophotography capable that I could explore with it. That's good as a starter, like iPhone and CCD and DSLR. Grab and go, because I live in the Congo. And then I kind of wanted to do the hard way, so I had no go-to. I just want to learn about the dials and polar alignment and star hopping, because, well, that's how I roll. So other people just like to slew their scope. My budget, I went for a medium budget between $600 and $1,200. And here's a little technical note about Q mounts. You can find this information online, but they use a right ascension declination system, which basically the telescope tracks with the rotation of the Earth. Practicalities. So I'm going to go over different types of telescopes, and those telescopes are usually designed for certain tasks. It doesn't mean you can't use them for other things, but you may have to spend a lot more money to make them do what they weren't intended to do. So the focus of this is a bit more narrowed down in those terms. So these are the different types of telescopes. So we have Dobsonian, Smith-Newtonian, Smith-Cassegrain, Maksutov-Cassegrain, Newtonian, refractor, Ricci-Chrétien. So I'm going to go through these one by one, so you have an idea of what they're all about. So the first one I'm going through is a Dobsonian. A Dobsonian is actually a Newtonian telescope on a Dobsonian base. So really when people say Dobsonian, they mean it's on this base. The Dobsonian has no tracking. I think it is an ideal telescope for someone who has no clue what they're doing and just want to look at magnetic things. This thing, you could get fairly decent sized scopes. They collect a lot of light, so you have a nice big light bucket. You can see things. The only problem is these things just rotate this way and up and down. They do not track stars. They do not even rotate with the stars. So you have to adjust it in places. The stars drift in and out of sight. But I think it's an excellent scope. It's easy to learn. You just point and away you go. Well, find your scope. So now, Newtonian. When I think of a Newtonian, I think of a Newtonian scope on an EQ when people say Newtonian. As soon as they say Dobsonian, I know immediately. So I'm going to misuse the terminology here, but basically a Newtonian on average costs slightly more than a Dobsonian on this type of mount. It's also a good beginner scope. It's just slightly more trickier than a dog. It requires balancing and polar alignment. But I've managed to polar align my scope with my cell phone. So it's done pretty good. I just take the compass, put it on the tray, and point the scope. One of these days I'll learn how to properly polar align it. So let's talk a bit about the optics. You have an aperture, which is the entrance for the light, and it bounces off this mirror, which is concave. And in this case, it's actually shaped like a parabola, its surface. And that bounces off this mirror to the focal point right here. So that distance from this primary mirror to this focal point is called the focal length. Now, the thing about this is more for observing than astrophotography because you get what's known as coma. You get these distortions on the outer side. I've never actually looked for this, so I don't know how much it is. And some of these smaller Newtonian scopes actually come with a spherical mirror, which I'll talk about in a minute about the type of aberrations. But it's a negligible effect for a smaller scope. Okay, so the next scope is the refractor, and this is an excellent scope in my opinion, but it can be extremely expensive for your aperture and your optical quality. Like literally, you end up throwing a lot of money to getting a really top-notch scope. And this scope is outside of my budget range. Just a decent scope is like $1,200. Tripod, another $1,000, then photography equipment. It just balloons. And I just mentioned here, this is here you can have a go-to on an EQ also. So that's your refractor, and basically you can see the doublet here that I had mentioned, and this one's designed for visual, as you can see, because of the two lenses. Whereas with the triplet system, you correct for that aberration. Okay. The next is the Schmidt-Cassegrain. So, I remember that I mentioned before about parabolic and spherical mirrors. Well, this is a spherical mirror, and you can see the light doesn't quite come to a focal point. But this effect here is very small for smaller diameter telescopes. So what that means then is these tend to be cheaper also. But as you get larger mirrors, you need to correct for that to bring it more to a focal point. That being said, this uses a spherical mirror, and then it has a spherical convex mirror, and then this corrector plate, which actually corrects, fixes the spherical aberration and some of the coma correction. Now, the interesting thing about these scopes is that they're a lot more compact for their focal length. So, when I showed you the Newtonian on the EQ, at some point, like an 8-inch daub is like this. So at some point, the telescope is so big that you'd have to stand on a ladder or a step stool to look through it. Whereas this one, well, you can look in the back, so that helps a lot. But it turns out, because of this convex mirror, it actually magnifies the focal length. So you get a lot of focal length packed inside a smaller unit. And this scope I tend to call a workhorse scope. I see it everywhere. It's a good all-round middle ground scope. A lot of people use it. There's a lot of used scopes in this category. Usually that orange one, I forget the company. Celestron, is it? Yeah. Classic. And then here's the Maksutov Cassegrain. So similar scope, except And this corrects for spherical aberration and coma. This is just by design that this tends to have a more compact focal length than the cassette ring. That being said, another thing to note, if you really want this as a grab and go, the practical upper limit in size is about 6 to 8 inches. Otherwise, you'll be waiting all night for your telescope to cool down to the environment before you can use it. So 3.5 to 6 inches, good. Cool down time is around half an hour-ish. In this range, it outperforms ST. Better optical quality, super portable, and, well, within my budget, it's affordable. But it has a very narrow field of view, which I'll also get into in a minute, and a high magnifying power, which I'll also mention. So the next scope is a Ritchie Chrétien. This scope is actually really used by scientists. It has a hyperparabolized mirror which corrects for coma, and you get astigmatism. The nice thing about this, though, is it's an ellipse. So it means you can calibrate your scope and you can measure the positions of stuff. Whereas that's much more difficult. So this scope, as you can see, it's got a convex mirror and secondary mirror, but there's a camera on the end because it's really designed strictly for astrophotography. Just about every orbital platform or terrestrial telescope is of this design. So I'll try to get the cost for the whole telescope. Yeah. And the other thing is, I don't really have a good example of it, but if you look in the front of a Newtonian scope, you'll see what's called a spider mount. So I put a little diagram here that holds that mirror in place, and you can get the fraction effects. That's what's here. But the scientists don't care about that because they understand that you can correct for it. So yeah. So it's really used for astrometry somewhere, which is basically measuring things for astronomy. Okay. So this one is more of an honorary mention. You can have different types of scopes. So this is a Smith Newtonian, so it has the Smith corrector, but it's a Newtonian type scope. And yes, there is even a Max Sutov Newtonian. I looked it up online. So just about any combination you can think of, you'll find out there. There's a patent for a telescope that has 6 concave mirrors. I don't think anyone's good. Okay. So let's talk about the field of view and F ratio. So this is really just a demonstrative diagram. So there's not really a scale on here. But say I have this 3-inch aperture here and this 15-inch focal length. Well, if we look at this and we pretend this is our moon here, we can see that this cone here is the field of view compared to this longer focal length here, 36 inches, where the cone is smaller. So this is a field of view, and because it's a large field of view, you're actually collecting more light for that field of view. But when it's smaller, you're collecting less light, but you're getting better magnification. And we tend to talk about that in terms of the F ratio. So you take the ratio of the focal length to the aperture. So this is an F5, you take 15 divided by 3, and an F12. So I will come back to this, because this is a very naive diagram, but it's to give you an idea about field of view and F ratio and light capturing ability. Okay, so can we do everything with one scope? Well, not really. If you want to see, let's see. Yeah, if you have a bigger mirror, you can see faint fuzzies, but you must just decrease the F ratio. Whereas if you have a longer focal length, you can see tiny things, but you must increase the F ratio. So there's this game that you have to play. You don't get the best of both worlds. You can get in between, but not the best of both worlds. And shorter F ratios they got more light gathering, makes it easier for astrophotography, and we tend to call these things light buckets. Longer F ratios, it takes longer to gather the light, so you have to have a good tracking system to take those pictures, so it requires more accurate tracking for planetary telescopes. Anything else there? No, I guess that's it. And so this is the basic telescope shopping parameters I have so far then. I have the F ratio, as we mentioned, so that's related to the light gathering capacity and so forth. But if you like, we're talking about focal length and aperture, so it's really related to the focal length aperture ratio. And then we have magnification, which is minimum and maximum magnification of your scope. So those are specifications you can find where the scope is designed for those minimum maximum magnifications. So this is my pricing chart. So I have here, this is 2019 pricing. So this is the price here, and this is the optical quality here. This is an honorary mention because my friend Michelle managed to snag this off Kijiji for $250, and that thing is wicked. It moves, it slews very fast. It's pretty cool. I did actually, it was discontinued in 2009, and I projected the prices using the stock market, and that's probably what it would be worth today if we tried to buy it brand new. So here's my budget cutoff line, and I really wanted something for planetary and sort of astro, you know, doing a bit of astrophotography, and that puts me right here in the Maksutov-Cassegrain range. These are more for visual astronomy, and then these are more professional scopes, more advanced scopes, but, and this one is really more for scientific imaging. So, one thing is you should be careful with the mounts and tripods. Now, there was one of comparable size on a spindly mount, and the thing is, so the thing I like about Google Images is you can quickly scan through the scopes and go, yes, no, right? So you can see, this will be a nightmare. Basically, you touch the scope and it will shake forever, or the drive is moving and the scope will shake. So, and in this price range, I have to be careful because you go, oh great, a go-to, so many inches, great, but then you go online and you look at reviews and you realize, no, people are really, really complaining that you can't see anything because the scope keeps shaking. So you can check the reviews on the website, but be careful because they sometimes put fake reviews. But Cloudy Nights is a great resource to go to. So quite often when I finally make a decision, I'll go there. Also talking to an RASC member is extremely helpful too. Right. Okay, so this is what I ended up getting. So I got an Orion Star Max F12, 127 millimeter aperture, which is 5 inches, I believe. 1540 millimeter focal length. So good reviews on Amazon and Cloudy Nights. I got it, this is the total Canadian with shipping and everything. I decided to order at keytelescopes.com because they're an Orion telescope dealer, they have warranties, it came double boxed and everything. Whereas if I order on Amazon, it could come damaged and their return policies are really tricky. So you have to look for a little sticker on there. So I've experimented having things shipped from Amazon. I don't mind shipping eyepieces and stuff like that, but I decided I would go with the dealer, and there wasn't that much of a price difference. So, these are the specifications. What am I doing? We're doing okay. So it says best for viewing bright deep sky objects, best for imaging lunar and planetary. And there's my optical diameter, focal length, F ratio. It came with one eyepiece, a 25 millimeter across the eyepiece. Magnification, 61 times of that eyepiece. Magnification range, 18 times to 254. This turns out to be somewhat impractical. Let's see. Just a side note, there's different types of mounting systems. I chose a dovetail system, so you may want to also research that. There's just so many things to research that eventually I just end up biting the bullet and ordering the scope. It has setting circles and polar axis scope included. No motor drives, I'll have to get one of those. So the motor drive, all it does is you point your scope, and it's called a clock drive, and it just tracks the stuff. It doesn't go to, it just keeps tracking. Fully assembled, 36 pounds, must have been all the weights. one eyepiece, the 25 millimeter Colossal was actually the choice. It was at least you would see a lot of things with this. It was a big choice. It really helps if you have a friend you can borrow their eyepiece kit from. It really, really just saves a lot of time because it's crazy. So I played with these eyepieces because I only had them for one night, and I was like looking at the moon and looking at Mars and looking at different magnifications. I didn't get a time to go through all the filters. So after playing, I decided that moon viewing at 32 millimeter is a great eyepiece. Middle ground, I chose 25 millimeter Colossal, but I chose a 17. And for planets, I chose a 9. And Darren really convinced me to get a 12 millimeter. And that thing I use quite a lot. I use it a lot for viewing. And then the 6 millimeter is just to see what my scope can do at maximum magnification under ideal conditions. So I haven't quite had those ideal conditions. No, but I've gotten down to my 9. So I introduced another concept called the magnification, which is the telescope focal length divided by the eyepiece focal length. And so I have a 1540 millimeter eyepiece focal length. Focal length of my telescope. So you just divide out by the eyepiece focal length to get your magnification. So here's my little table, and you can see my magnifications here: 6 millimeter, 257, close enough, 32, 48. And if you remember, that's right. Okay. Actually, the number where I said was impractical, I meant the 18 times magnification, the lower magnification. Turns out this is about optimal. Any more, you don't get much field of view. Like I could go to 40, I could go to a 40 or 70 millimeter focal length, and I'm not getting much more field of view. Okay, this turned out to be something very important for me. And the funny thing is, if Darren didn't give his talk about eye relief, I would have never thought, ever thought of this. But those low magnification, the high mag eyepieces, I find myself constantly bumping my eyes and seeing my eyelashes. So that became a real sticking point for me. This is actually a summary of Darren's talk, and it's eye comfort parameters. So I'll put this here. And it really depends on your age, because as you get older, your pupils don't dilate and contract as much. So, and if you're wearing glasses. So the eye relief, so here you can see, here's the person's eye, and this is an actual eyepiece that's inserted into a telescope that's out down this way. Now the eyepiece actually has two focal lengths, one this way and one that way. They tend to be symmetric, but they don't have to be. So the distance between the eyepiece and the focal plane where it enters your eye is called the eye relief. And the exit pupil is basically related to what's getting into your eye, okay, in that field of view. So you can actually get the exit pupil by the focal length of the eyepiece divided by the F ratio. And I chose a 15 millimeter eye relief. That's because also I got to play with the eyepieces. And glasses recommended 18 to 20, but even my friend can use the 15 with her glasses, so it seems to be pretty good. And then the exit pupil. Okay, so I just want to go back to this true field of view concept. So what I've done here now is, because you have to be careful, the eyepiece has its own field of view. So when you look through an eyepiece, and this is just a one lens eyepiece, but it just gives you the idea. You look through and you see this large field of view. And this is called the apparent field of view. And if you look here, you can see there's a field stop diameter, which limits the light going in there. And so if you take the field stop diameter, divide by the focal length, you get the apparent field of view. The nice thing about this diagram is if you're bored, you can actually calculate these from that diagram. It is somewhat exaggerated. You have to picture this off at infinity, so this isn't as small as it looks, but it is smaller than the apparent field of view. So it's the telescope with the eyepiece that gives you your true field of view. Together, the combination gives you true field of view. And that true field of view is related to the field stop diameter, which is here, divided by the focal length. There are other formulas I will show you later, but these are the So, so the point is here, I'm looking through this eyepiece, and then I'm looking through this main objective, and I'm seeing a star on the edge of my field of view, and so that gives me the true field of view, what I can see. Okay? So, eyepiece shopping criteria. So I decided to budget about under $100 an eyepiece, mainly because I'm willing to pay for that eye relief. And also, the nice thing about eyepieces, you can use them in any other telescope. Well, with the 1.25-inch thing, which most people use, opening. So it is a good investment. Well, that's part of my justification. So, and it turns out also that Maxitos, especially the one I have, is very forgiving when it comes to eyepieces because it corrects for a bunch of things. So I really don't need very expensive eyepieces. And like, for example, if you go on Google Images again, it's actually kind of cool because you can immediately tell by looking at the amount of glass in the eyepiece how much it costs. So that's a very expensive $243 eyepiece, which probably flattens your field and corrects a bunch of things. Although I read on cloudy nights, why don't you just line up your object and look straight down the middle of the eyepiece? Save the bottom. Yeah. So my price range is here. So I was actually able to quickly parse out what I wanted. And then I have this table here. So these are my. So I want 50mm eye reliefs, and my application is moon and similar sized objects, middle ground, and planetary maxed out. So moon, so if you want to look at the moon and the sun, you need a large field of view if you want to see the whole thing in your scope. If you want to see planetary, you really want a narrow field of view so you can see more detail. And then I just wanted to max it out, so I got the narrowest field of view at that range. So, before we get on to the shopping, I've actually just went through every one of these equations except this one here where you take the apparent field of view and divide by the magnification. Most eyepieces are specified this way so you can get your true field of view calculation. I wouldn't be overwhelmed by this. I mean, I took 2 months researching this. People have taken more, so take your time. That being said, all of this you can just plug into a spreadsheet once you figure it out. Okay? And so, that ninth picture I had of the field of view, well, this is a more complicated picture. You can see it really depends on the optics, the aperture, and the field stops, and a bunch of other things. But you get the idea. Okay? So this is sort of a detailed diagram of all the notes. So we just pop that into a spreadsheet. Here's my spreadsheet. And so I went online and started shopping, and I had a conversion from Canadian to US so I could get my budget. And let's see if I can find a good example. Yeah, here's in the 12mm category, the planetary. If we go over, you can see here's the eye relief, 15, 16, 15, 20mm. No, don't want 20, I want 15 or 16. True field of view, in this case they're both comparable, but I'm looking for the narrowest possible field of view, so in that range. What else? But you can see up here, you can see how much the eye relief varies or the field of view can vary. And then the other thing is the 32mm, if I look here, you can see the true field of view is about 1 degree. And in fact, if I keep going up and up and up, it really doesn't get much bigger than that. So that's kind of a limit to the size. And the 32 is the most popular piece, so it's easy to get your hands on, except for a 15mm eye relief. That was tricky. I found some guy online who had a spreadsheet full of thousands of eyepieces, and then I just pressed a few tabs and found the graph. So over here is the checklist of the ones I chose, and I chose them based on the criteria on the sheet I have in the back, the type of objects I wanted to view and look at. So total cost of shipping, duties, mysterious duties, some get duties, some don't get duties. I don't know what's going on there, but so that was the total. So that's basically on budget. Well, not exactly. This is 1, 2, 3, 4, 5. Slightly over budget, but there you go. Okay, so shield. And that thing's come in handy many times, otherwise my observing nights would have ended soon. But basically, you have a certain amount of moisture in the air, and below a certain temperature, the moisture starts condensating on things, such as your primary objective in your scope, and now you can't see anymore. So this actually helps prolong that from happening. In fact, your whole telescope gets dew on it, but you're still observing. So that's a very important thing. You don't have to buy one, but I just kind of like this one. You can make them very easily. Then I want to do some solar observing, so I have got a solar filter. I should just say never look through your scope without proper solar filters. And if you're not sure, please ask someone. A friend of mine mentioned once, for instance, you see, oh, H-alpha filter, so I can see the sun. Oh wait, it's a planetary H-alpha filter. That's a big difference. You have to be careful. So it's good to ask about these things. Yeah, so there it is on the balcony. It turns out I can watch the planets on my balcony, which is great in the city. So that's really nice. And then I picked up a clock drive so that I could track things. And I have a little thing for astrophotography. These are actually videos. They should start working, but they haven't. So, but this is of the sun with clouds going over it, and this is Saturn. And this is my collection of iPhone photos that I've taken so far, and that's Mars. And then this isn't really buying the moon. It's just the planetary filters, moon and planetary filters. It's funny how much I spent. So, turns out.
They're moving.
Oh, there you go.
Took a while.
Slide is going to transition. That one will start moving in the second after.
Is that a cloud or do you have a power line in the way?
Oh no, those are clouds. It's kind of cool. Yeah. It was setting. So, there we go.
There we go.
Yeah. So, and then you can stack images. Okay. So it ended up costing me. In the end, it ended up costing me $2 grand. Twice my budget. I blew my budget. So it's not just the scope. You can expect to spend as much in the accessories as your scope, which I really never thought about. Luckily, I did buy all the stuff over a period of time, so it wasn't a huge hit, but still, yeah. So that was one of my lessons learned. So, in summary, you should really decide what you want to do with your scope. That's the big question. Then ask yourself, what's your budget? Be aware that you can expend as much in accessories as your scope. There are sites that offer financing. Telescopes.com allow you to make 3 monthly payments without interest on my scope, which is nice because I don't like to blow a lot of money in 1 month. I like to budget, according to, So that really helps. And then I didn't buy all those eyepieces at once, all the accessories, so it was over a period of a couple of months, so it doesn't impact you as much. Would you be okay with that price if it turns out to be a coat rack? And for me, I was like, it's a nice scope. If I don't end up using it, I'm sure I'll use it occasionally, so I'm happy with it. But it turns out I use it a lot more than expected, probably because it's easy to set up, easy to take, grab and go. Do your homework. Seek help. You can go on cloudy nights. You can talk to RASC members. They're very helpful, very experienced. Take your time. I spent 2 months researching this and pricing and everything. And some people spend even more time. So I think it's important to take the time. I'm hoping this thing will serve as a roadmap for everyone, for new people. The process. So I've summarized a lot of the things here. There are other details, but this is basically kind of it, kind of the approach. So I'm getting a lot of enjoyment out of my scope, and I hope that you do too. So clear skies. The smartphones these days can compensate for that. So my iPhone has a little window. You line it up in the window, and then you can dial down the intensity I did try filters, but I don't need them for my smartphone.
What about just observing?
Only for the moon. The moon is very bright, so you should get yourself a moon filter. They're not that expensive, and I think it's well worth it, because you feel like the back of your eye is slowly burning when you look at it. It's that bright, so.
Easy to find, huh? You hand over the eyepiece and then suddenly, oh, there's a flashlight in my telescope.
Yeah. Other questions? Yes?
Have you tried borrow lens with your eyepiece?
Only recently.
That's a great thing, isn't it?
Yeah, well, yeah, if you get good borrow lens, you can reduce the number of eyepieces, because a borrow lens multiplies the magnification by 2.
2 or 3.
Yeah, 2 or 3. I did use it foolishly once because I wanted to see what Saturn looked like at 650 mag.
Yeah.
That was cool. It was like huge but very fuzzy.
It's fun too.
Yes, but it seems to upset a lot of astronomers. Like, why would you do that? It's useless. Blah blah blah. But it's just cool. It's like it's huge.
I like it to use a larger magnification eye, or a larger focal length eyepiece to observe planets, because you don't have a tiny people eyepiece, so really expensive.
But the 12 and 9 are the best. Most nights I can use the 12 and the 9.
Yeah.
There was one night where I had to go to the 17. The atmosphere was so unstable. I've used the 6 a couple of times, but the atmosphere's never quite been there for it. Yeah. Other questions? Yes.
So I've got a 5-inch Mac, and I've got a 25 and a 9. And if I were to get one more eyepiece, which one would you get?
It depends on what type of eyepieces you have.
Just a 25 and a 9.
A 25 and a 9, probably a 32.
32?
Yeah, well, the 9 would be good for planets, I guess.
Yeah.
It's kind of on the limit. The 25 is a good all-round in between, and the 32 is good. But that being said, it also depends on the focal length of your scopes.
1500.
Yeah, but they're not all 1500, right? But I think of those, it's fine for any scope in that particular case. So I would get a 32. That's if you want to put the moon and stuff like that.
Yeah.
Other questions? No? Okay, well, you can poke me at the break time if you like. Other than that, I guess we can move on. I don't know who's, oh, there you are. So, thanks.
Hi everyone, thanks for coming. It's just kind of like, I guess winter's here to stay now. Let's hope not until December that we get it. I'm Brian Stach, your club president, and I'm also the director of Glenlee Observatory. Weather for tomorrow doesn't look very good. Anyways, this is what we have lined up for today. Of course, we have Jay Anderson with what's new, Danielle for what's what's up? Sorry, I got that mixed up. All right, I'm just going to move on. I'm not having a very good day here. Oh, I had a rough week. Even went to the concert last night at Fleetwood Mac. Courtesy of the CO.
Poor you.
I know, it's a tough life.
So much sympathy. You posted it on Facebook too. Hi.
Club seats, or box seats, I know. Anyways, the CEO actually showed up. Okay, so the open house for U of M. What do I have? November 27th. Okay, so I think that's the last one for the year, I believe.
Yeah.
It is, okay. All right, so I'm planning on to be there. Hopefully the weather is good. They have some interesting topics, and plus they have some telescopes there. They have the LX200, 16-inch, I believe. So, and there, we also have the Old Comic March coming up in November, the 21st. Again, weather permitting. But we have a little presentation on observing. I don't know who's doing this. It might be Sheila. I'm not too sure, but I get confirmation on it. But anyways, if you bring a telescope, you can waiver the $10 fee and enjoy the night. More astronomy for some of us. All right, transit of Mercury. This is coming up this Monday. I saw the email going out. Darren's doing Birds Hill Park, and Dennis is doing Glenley. I'm planning to be out there too. Monday morning, I think we're planning on a breakfast too. We're going to probably make head out, but we'll keep you guys posted. The weather still looks good. I just checked just now. It's supposed to be still sunny on Monday, and hopefully we'll have a good time there. What else do we have? Okay, the RSC meal list. I was going to update this and have this on a handout for everyone instead of me repeating everything every time I come up here and try and do something different. But anyways, so November. Anyways, okay, calendars. Abdul, how many do we have left?
We have 25 left.
25.
25.
Wow. Okay, I'm definitely gonna get mine today. I got money. So, anyways, this is a really nice calendar to have for us as astronomers because it tells you the face of the moon, tells you the meteor showers that are going on, and all that. It's really good info when the sun sets, when the moon rises, and all that. So this is a really good calendar. I keep it up. Like as soon as I wake up, it's there, so I know what's going on every single day. And it's only $14, so it's a pretty good deal. All right, we have to explore the universe. Dennis is here, so if you have any questions, please see him. It's a really great way. He's in the back. It's a great way to get to know the skies, a little bit of star hopping. I think one of the questions was, do you have something to say?
Yeah, I'm curious to know if any of these people in the room tonight, Kevin Gummer, and the other person that's with him, Corinne Robinson. And I got one more name to call out, and then I'll tell everybody why I'm doing that. I think I have his name on it. Okay. And Robin Clark. So those three people
congratulations for those people. All right, of course, we have the telescope loan program. Abdul is in charge of it, so if you want to come see him during the break, please do. I don't know what telescopes are available, but
We have the dog right now. I like one of them.
okay.
That's one.
All right, that's all we have, but we'll have more. Actually, we should have a list. I'm just thinking of what, I talked to Jay about some things that we should do. Okay. Okay, this is just an idea of what we have. This is really nice that PST comes with this tracking mount. So it's really nice. I get to see the sun in real time. Glenlee Observatory, that's me. I'm director of Glenlee, as well as the president. So I'm really booked for the rest of my life. So anyways, we have the 12-inch. We do have other telescope, which I haven't got around to it. I was hoping to do it. We do have a 6-inch go-to that we put on the wedge there. But anyways, if you want to come see me, I do have a few keys cut. There'll be a $10 deposit, refundable if you return a key. Of course, I'm more than happy. Every time I'm out there, I'm more than willing to give you guys a little tour of Glenlee and how to use the LX200. Last time we did it a couple weeks ago, it worked really well. Telescope functioned really well, and it was gray skies for the most part of it. So, so that brings me to, well, that's some of the features that we have at Glenlee. We do have lots of coffee, lots of tea, so I got that from work. My boss gave it to me. We probably have 50, 60 of those. So anyways, this is the guy scope that we have here, and of course the classic LX200.
Hey Brian, sorry to interrupt. I was just going to say, the LX200, is it configured for solar as well? That is? You know?
No, it's not.
Okay, I wasn't sure. Like, I know you guys are hosting the solar event. I just wasn't sure if the scope was set up.
Yes, I think we talked about that. Okay, so anyways, this is some of the controls that Brian Greenberg was working on earlier. This is also the control that mimics the warm room. So the goal is you can actually control the LX200 in dome from the warm room. And during the winter time, you can just sit there and have a cup of coffee and let the telescope do the work for you. All right, cancel. Forget it. I looked at the weather, and it's snowing tomorrow. So it's not going to happen. This year has been really poorly for observing, so we'll take what we can. Hopefully, maybe next week I'll have something going, but we'll have to wait and see. What else? And that's it. All right, moving on.
Hey, just before we do the other talk, can I just interject for a second? For those of you that are planning on attending, not attending the Glenlee and going to Birdskill, I'll do an announcement on Sunday. I'm going to probably make the criteria a little more strict than the guys will at Glenlee because of the fact that we don't have access to a warm room or facilities. So if it's exceptionally cold that day, we may not do it. So I just thought I'd let you guys know. I'll give an update to everybody that's on the list. For those that are interested in doing Birdskill, probably mid-afternoon Sunday. We'll have a better idea.
Road condition too.
What's that? The road conditions. Yeah, and the road conditions too. But I mean, I think they'll probably be okay, but we'll see. So I just thought I'd let everybody know. Okay, thank you. What's that?
All right.
Site 2.
So moving on, we'll start with. I think we'll start with Jay first.
Before I get too far into this, Brian canceled Saturday, so the transit will now be on Tuesday.
No, that's how it works.
Manage my things. Well, I've known people at solar eclipses that, well, let's just say cruise boats that were heading out to solar eclipses on a long day in the wrong place. Okay, what's coming up in the next month? Well, I'll start with showing you what the sky would look like if it would ever clear off. So this is tonight at 9:11 p.m. and kind of stretched out because of the program has wrapped the horizon in a bit of a circle there. But as you can see from this program, or this kind of view that it's given us here, that we have the Milky Way stretching across the sky from the east in here, or the west in here, across to the east, and the sort of thinner part of the Milky Way is up through Cassiopeia and Cygnus, and more or less overhead, or close to overhead, on tonight in another couple hours. And then there are a couple of things that are fairly prominent in the sky, even from the city. We have some of the brighter stars, Capella here, this one, and Aldebaran in here. We have Altair and Deneb, which are more familiar to us in the summer. So in the middle of it, we have an absence of really bright stars. And when you get into a dark sky like Glenley, the square of Pegasus is probably one of the more important benchmarks. It's not that bright, but when you find it, it sort of leads you on to all of the other things. Unfortunately, tonight we have this thing, which is getting in the way, even if it were to quit snowing and turn into clear skies. Now, if we take a look at 5 o'clock in the morning, because, of course, the Earth is rotated a little bit, so the western side of the Milky Way has gone and set, and what we would call the winter part of the Milky Sky is now more or less running from the south horizon straight up. And we can see here's Capella has now rotated from its position over there to be more or less straight overhead, or at least on meridian. And you can see we have a number of much brighter stars here. Big use in Orion, Rigel and Orion. Orion has the distinction of being the brightest of the constellations, so it's easily seen from the city, for those of you who are up at 5:19 in the morning. In Gemini, Castor and Pollux are bright stars, Regulus in Leo, and Arcturus is coming up in the east, probably a little low for a decent view. And you can see the constellations, most of you would be familiar with because they're the constellations, the various horoscopes, the zodiacal or zodiac constellations. Now, I've drawn two lines on here. One of these is called the ecliptic. That's the gray line. That's the path that the sun would take. Of course, the sun is on the opposite side of the skies, but you can see, well, I can't see it, but at various points along here, there are markers of the season. So the sun would be in this area in April and May. And of course, the dark part of the sky would be the part the sun is in now. The other line that I've given you here is the Earth's equator, as it was projected up into the sky. And these are kind of interesting reference lines, particularly this ecliptic or path that the sun takes, because the planets that we see are always going to be close to the ecliptic. Now, if you're up early in the morning, of course, there's some very nice things to look at. Right in here is the sword hanging under the belt of Orion, and that's the Orion Nebula, which is one of the brightest nebulas that you can see. And the Orion Nebula is usually kind of the first target for any telescope or for binoculars, and it actually lends itself rather decently to a 10-second exposure on a digital camera if you're sitting on a tripod. Well, it sort of shows you what the skies look like as you go through the night. At the end of this time that I'm discussing, this day in December, you can see that the evening sky now, the eastern, the western part of the Milky Way has set. The eastern part is now a little further advanced along. We're getting more into the winter type constellations, or at least the fall, the winter constellations. So you've got Aquarius and Taurus and Gemini and Cancer running in through here. And surprising because the moon has approximately monthly cycle, so it comes back to the same place. But at 9 o'clock in the evening, a month from now, Orion's starting to get up pretty decently in the sky, and that would be the constellation you focus on most when you're looking from the city or from the countryside. There's some interesting things to see up in here in Cassiopeia and Perseus and Auriga, with binoculars in the case of Auriga and with small telescopes otherwise. I want to talk a bit about the planets this month. Well, there's not anything spectacular in planets, but there are a couple of developments occurring that will make them more spectacular in the months that come. By the time the sky gets dark tonight, you can see Venus is very low down on the horizon here. Now, Venus is exceptionally bright, so even when it's very low, it's often easy to see if you've got a good view of the, in this case, the southwest horizon. You can see this is the ecliptic I've left here, and we've got Venus and Jupiter and Saturn along the ecliptic, not exactly on it, but close to it. So that's really what is important. Jupiter is, this is at relatively early. The star park program is showing the sky still slightly bluish. I think this is about 5:30 or 6:30 in the evening. And so it would be difficult to see Jupiter with sky that bright. It would be visible, but it's low down. It's only something in the neighborhood of 7 degrees high at this time. And then by the time it gets darker, Jupiter gets close to setting. So it's really not well suited for observing right now unless you desperately have to have a look at Jupiter and the moons. Saturn's a little better placed at 10 degrees high in the early part of the evening. And if the skies are nice, it's probably be one of the first targets to go after because the rings of Saturn are nicely displayed right about now. However, by the end of the month, you can see that it's getting down low, close to the horizon, and it'll be fading out from view. Now, the one difference between Jupiter, Saturn, which are moving this way as the sky is moving that way, taking them with them. Venus in its orbit is actually moving back this way. So Venus is going to be getting better and better as the month goes on, while the other planets get worse and worse. But at least for the next month or two, Venus is still pretty low down in this part of the sky, even though it's moving away from the sun. And it's not going to be really good. But it will be really excellent when we get into February, March, April, May. We get to Uranus and Neptune, they're the ones that are sort of up highest. They're sort of straddling the moon tonight. But you have to be a little bit dedicated to find them. A month from now, they're going to be in approximately the same location. They'll have moved a little higher in the sky. But they'll still be the ones that kind of in the sky for the whole of the night. They're an interesting exercise to find them. Especially if you have a go-to telescope and you just have to type in Neptune and then it'll go to it, providing you have it calibrated. Tomorrow, now we get to Mars, it's rising just about the time it's starting to get dark, and, it's starting to get light. It's about 2 hours ahead of the sun, and then a month from now, it's 3 hours ahead of the sun. So Mars is starting to come out from behind the sun, and will eventually, in a year, be very, very nice planet to look at again. But at the moment, it's only 4 seconds in size, so it'll have to be pretty dedicated to even see anything more than what looks like a red star. Mercury, of course, is right on top of the sun on Monday, and you won't be able to see it again until you get to December when it comes out from behind the sun in the morning sky. By the time we're looking here, December 9th at 7:20 in the morning, so you can see Mars is about 17 degrees high. It won't be very bright either, and Mercury has now come out from behind the sun and is 6 degrees high. For those of you who remember the talk I gave 1 or 2 months back, the ecliptic here is now at a much sharper angle with the horizon, so planets come up very quickly up from the horizon as they're moving shallow angle. So depending on where you are in the ecliptic, your visibility improves pretty quickly. I gave you this last time. I won't say anything more about it if you absolutely need timings, but this is pretty simple. It's from sunrise till noon. And all you need really is one clear patch in the sky to be able to see it. If you want exotic photography, you'll need more than just one clear spot. Of course, the reason why Mercury is on top of the sun is this is the orbit of Mercury, the red line here, and this is the ecliptic, or the path of the sun. And they happen to cross each other, but they would do that every month or every orbit of Mercury. Well, we also, which is where the view is taken from, we are also on that straight line joining all of them, and so we're effectively getting an eclipse with Mercury. Venus here, its orbit follows this other line, which passes above the sun. So Venus would have to get into the same position at the right moment, which it will do in another 110 years or something like that. Seeing where it's visible, you can see that we don't see the entire transit. We're a little bit off this part of the curve here, so it's already underway by the time it rises. And that could be a very nice picture if it's clear on the horizon. A sun rising, maybe even the sun that's a little bit of a football shape with a tiny little dot of Mercury in it. But you're not going to see Mercury. I don't even think it will be visible in binoculars. You're going to need a properly shielded telescope to see it. It's a pretty tiny dot. Here's the forecast for Monday morning. Let's see if I can read. This is Monday here, and this is midnight Monday, and this is noon Monday. So the computer model here, this particular one is saying something like 30% cloud cover. And these are the cloud cover maps from two different models. This is, for those of you who follow it, this is the NAM, the North American model. And of course, we're right in here, so it's showing generally clear skies. This patch of cloud is probably a streamer off of the lake, and it's the same patch that's here as a streamer. So the different model, this is a coarser long-range model, this is a short-range finer model for both American models. And both of them say that there's a pretty good chance we're going to have some nice skies in the morning. And there was a question about temperature. This is a temperature curve here showing temperatures around -8, something like that. Now these are computer model temperatures. Usually the actual ones issued by the weather office will be a degree or two warmer or colder than that. And this is, if you were to photograph the whole thing, or as much of it as you could, you'd get a picture like that if you assembled them all and put them on top of each other. And that's about the size that Mercury will appear, so it's tiny. It's not going to stand out like Venus did in 2012. What else we got going on this month? Well, we have the peak of the North Pole meteor shower. That's a couple of days from now. The long shower. I think some of us have seen the odd meteor from that shower, but sometimes they're quite bright. A nicer shower is the Leonid meteor shower peaking on the 18th. And I'll have a little bit more to say about that. It's a favorite of ours, but again, it's not a particularly populated shower. On November the 23rd, Jupiter and Venus are close together in conjunction. That's the way they will appear in the morning sky, or in the evening sky. So even though they're very low down, both of them are bright planets, so they should be susceptible to a nice little photograph if you can get a view of the southwest horizon. 5 days later, the moon will be in with them. By that time, Venus will be up here, Jupiter will be closer to the horizon, and the moon, I think, sits in between them. Then November 29, we get Saturn and the moon side by side because the moon moves up this way and comes to pass Saturn. This is what it looks like. Well, December 8th to 12th, so it's over a 4-day period. Saturn and Venus will pass each other. Saturn's fairly faint, so you're probably going to get a better picture on the 23rd of Jupiter and Venus passing each other. The Leonid meteor shower, it has had some spectacular storms, but one isn't due for another 65 years. But typically about 15 per hour, and sometimes you get small outbursts. You can see what we do like about the Leonid meteor shower, especially if you're doing photography. You get occasional really nice fireballs and persistent trains that might last for 15 or 30 minutes. So the peak is the night of the 16th to 17th, but we got this big bad monster sitting there, so you might want to get out pretty early in the night if it's clear and you want to have a look at that. And that wraps it up, except for the cat.
Next, we have Danielle for what's new.
Hey. Hello, everyone. For those of you that don't know me, my name is Danielle Pahut. I'm an instructor here in the Department of Physics and Astronomy. I'm also in charge of the Lockhart Planetarium. So the first what's new that is not related to anything sky-related is that the new planetarium hit customs today. Yeah! This has been at least 2 years in the making, so I am pumped. The whole building smells like spackle. So we're currently on schedule for an early 2020 opening. And so we'll probably be transitioning the open houses from the classroom that they've currently been happening into our new planetarium. You're all more than welcome to come. And I'd love to see you there. So without further ado, what's new in astronomy? So I've got 3 articles that piqued my interest this week. So the first is that observations confirm lensing planet, which was originally discovered by an amateur astronomer, which is a lot of fun. I keep trying to tell my students that they can make a real science discovery. And so this is an article published in Sky and Telescope by Monica Young, who was a classmate of mine at Boston University, which was fun just a few days ago. I spelled flare wrong. I'm going to blame the autocorrect, but there was a solar flare. Those of you that have heard me speak before know that I'm a big fan of all things solar, and so I'll talk about the solar flare and it kind of being a herald of solar cycle 25 and why that's exciting. And then finally I'll talk about bubbles and heated clouds, which may point to a more active past for the black hole at the center of our galaxy, using MeerKAT. And this is an article written by Neil Carlisle, also for Sky and Telescope. Okay, so the first one, observations confirm lensing planet discovered by an amateur astronomer. And so the amateur astronomer was Tadashi Kojima, and he was monitoring a star field in Taurus back in 2017, looking for novae. And he did find a star that was brightening, and so it was kind of consistently decreasing in magnitude, which means getting brighter. And so on September 2nd, it had a magnitude of 13.0. On October 25th, it had a magnitude of 11.7. And on Halloween, it had a magnitude of 10.8. And so it is very faint. And so this little guy right here is Kojima 1, which is the variable star that he found. Yep. Okay, so he called for follow-up observations by the American Association for Variable Star Observers and the Central Bureau for Astronomical Telegrams. They've named it Kojima 1, and they have since done a lot of follow-up studies and have discovered that the variability in brightness of this star is due to microlensing of the star from another planet. And they've actually found a signature, it's microlensing light from a different star, but the light curve suggests that there is a planet orbiting around Kojima 1. So the follow-up observations were led by Akihiko Fuki at the University of Tokyo, and they used 13 ground-based telescopes spread around the globe to build up the light curve for this star. Light curve just meaning brightness as a function of time. And they also took some spectra of this star. And so the data that they collected is consistent with the existence of a Neptune-mass planet orbiting that star, and because the star is placed on the outskirts of the galaxy, so is the planet. And so this is published November 1st in the Astronomical Journal. Okay, so forgive me if you are already all experts. I've been doing a lot of teaching this semester, but gravitational lensing, recap 101. So if you have a bright star, which is the yellow one in the background, so on your left, and the light travels in a straight line in flat space-time to observers on Earth. If you have anything that has mass that gets too close to that line of sight or that line of travel for the light, then the mass is going to distort the space-time. The straight line in a curved space-time is actually curved. And then it may allow light that's traveling in slightly different directions to be deflected back towards us. And then something gets lensed and appears brighter. And so if there's a mass, in this case the red dot at the center of this graphic, will distort light, and because light that had originally been not traveling towards us will get focused towards us, that star will instantaneously appear brighter. And then as that red star keeps moving away, then the lensing effect disappears and the star goes back to its original brightness. So that's if you have two stars, so a star and a lens. It's all sorts of galaxies, it's the same physics, but on a different scale. And so in this case, we have a distant star, and then we have the Kojima 1 star, which is doing the lensing. But if you happen to have a planet, then you get what's called microlensing, and you get this extra little hiccup on that light curve. And so here, I have the scenario that I just described, where we have a bright star, a fainter lensing star, and a light curve, so the brightness is a function of time. I'm sorry that this keeps popping up. Is this a laser pointer? This one? Okay, here, so we've got brightness as a function of time. And so you can see that for a lensing event, you're just going to have an increase. If this star happens to have a planet around it, then it's going to have a much smaller effect on the fabric of space-time, but it will still have an effect. And it will create this little microlensing effect. So you'll have the lensing effect due to the star, and then this little extra blip due to the planet. And so if you see something that looks like this in a light curve, you can think, oh, maybe there's a planet orbiting that star. If you just have a random planet that has been gravitationally slingshotted across the universe on its own, you're just going to get a really small signal that you'll probably only ever see once. So we've done follow-up observations. I had nothing to do with it. So this team has done multiple follow-up observations and has built up the light curve for Kojima 1. And so here I have light curve, so this is residual magnification as a function of time. So each of these segments are segments of 20 days. And so here everything in black is the original observations, Kojima's observations. And then everything in color is the follow-up observations made by different telescopes. And so the telescopes are in different colors, so there's some coloring there. And then the blue line is a model saying if I have a star and a planet of a certain mass orbiting at a certain rate, this is what the light curve should look like. And so this top graph is showing you the observations. So you can see this light curve with this little dip. So it's not in the same direction as the example or the schematic that I showed previously. But there's still this little hiccup on the light curve that suggests microlensing. And you can see that the data, well, the model fit the data very well. This row down here is the residuals, which means if I take the difference between the model and these dots, what's left over. And so we can see that overall it's pretty close to zero, and there's some spread right around this microlensing event. And so here we've zoomed right in time. So this is 857, which would be right here. This is 860, which is right here. So we're really just zooming into this area. And you can see the observations and the model in blue. And so they've managed to fiddle with the parameters of the model to really get good agreement with the data. And these black arrows just indicate when and what instrument took spectra of the star. And the spectrum of the star allows us to determine its spectral type, so its mass, its temperature, things like that. Okay, so we were able to fit the data well enough to be quite confident that this is indeed a planet. And so we called it, the name of its star with a B, because that's how we name planets. Exoplanets, because there are going to be a lot of them. Well, there are already thousands of them, but this is the naming convention that we use. The L, I think, is because it was discovered via lensing. I'm guessing on that one. I'll be very transparent. I'm not 100% sure. The planet designation is Kojima 1LB. The mass of the planet that fits the data the best is a mass of 20 times the mass of the Earth. So this is a Neptune-type sized planet. And its orbital distance is 1.1 AU. And so we have a Neptune-sized planet that is very close to its star. From the spectrum, we've determined, I say we like I did it, I'm sorry, they determined that the star is much less massive than the sun, and so it's a, I think it was a K or M star, which means it's much cooler. So the habitable zone where liquid water could exist is much closer in. So even though this Neptune planet is at 1.1 AU, it is right at the ice line. So it's kind of right where water and other gases are condensing into vapors and ices. So beyond the habitable zone. Okay, so microlensing is one of the relatively newer ways of looking for exoplanets. And so astronomers monitor the sky and watch for such microlensing events. We have found 84 exoplanets using this method, which is great. The transit method, in comparison, has found about 3,500. So this is a sneakier, trickier method. Kojima 1 is also unique even within the microlensing, the exoplanets that have been discovered via microlensing. Most of the microlensing exoplanets have been discovered towards the center of our galaxy, because there are a lot of stars, a lot of things passing in front of each other, so there's a lot of lensing events. Kojima 1 is in the anti-galactic center direction, and so it really was quite fortunate that we caught it. It's also a lot closer than a lot of the exoplanets that we have found via microlensing, and so it's only 1,600 light years away, whereas the galactic center is significantly further than that. Okay, any questions about that? Yeah.
So what do they think is causing the microlensing?
Oh, so it's like an extra deformation in, so the star will deform space-time, and so does the planet. And so if you have a light beam that's coming through this system, instead of just getting deflected kind of quote-unquote nicely like this, it now has two masses to kind of maneuver around. And so as the planet orbits or is in different places, it will lens different amounts or different ways.
So that's a different star that's in between us?
So this,
So that's a distant star, and what you're saying then, Danielle, is that the other star, this
the Kojima 1 is
Kojima
lancing
1
in.
just happens from stellar drift to be going in front of this distant star, and that's where we're seeing the lensing.
Yeah.
But it's just, but you can only probably get, I'm assuming you can only get that data kind of one shot kind of thing, because the chances of them lining up are gonna be gone after that, right?
Yeah, or at least once, like at most once a year. Or less, yeah.
So you'll only get the micro lensing really when the planet lines up with the star and the distant target, because then you get the gravitational boost.
Yeah, I mean, I think that you might get a microlensing signal when the planet is in different places, but it won't look the same every time. Yeah. Yeah.
Yeah, so at the beginning you mentioned that the amateur astronomer was looking, thought he had found a variable star. And so is it both a variable star and also doing this lensing effect, or was the variability caused by the lensing effect?
The variability was caused by the lensing effect.
Okay, so it's not a true variable star.
As far as I understand it.
Okay, and then one other question on one of the later slides with the graph on it, you had LCO on the right. LCO second, what is that?
Those are, I forget exactly what the LCO stands for, but these are different observatories or instruments. And this is when the first spectroscopic measurement was taken of the star, the second spectroscopic measurement, and then another spectroscopic measurement with a different instrument.
Oh,
Yeah.
all right, thank you very much.
Yeah.
When the amateur astronomer was first detecting these increases in the brightness of the star, would he have been doing that visually or with some kind of software?
That is a great question. I'm not sure, to be honest. I'm sorry. I have the, I think one of my references is actually a paper where he's first authored. So he might go into that more. I didn't get a chance to read it as closely as I ought to have. So. Any other questions? Okay. On to my safety blanket subject. My thesis is on this one. So we are currently deep in the solar minimum of solar cycle 24. And so a solar cycle is roughly 11 years, and solar minimum is supposed to last, 2 to 3 years. The past few have lasted significantly longer than we anticipated them to, and have been deeper than we thought we knew that they would be. And so solar cycle 24 was a weak solar cycle, and it's had a deep, long minimum. And so the fact that the sun is kind of coming out of it now is pretty exciting. And so this is an image of the sun today by the Solar Dynamics Observatory. You can see that there are no sunspots. Very boring. This is classic solar minimum, deep solar minimum sun. In case you need a reminder, the solar cycle is often charted by the number of sunspots on the sun at any given time. And so for the past more than 100 years, there's been this relatively regular 11-year cycle where we get a lot of sunspots, and then at solar maximum, it declines, and then there's this short solar minimum, and then it jumps up. And there is a lot of variability from cycle to cycle. Cycle 16 didn't have quite the same maximum number of sunspots. But the minimum after solar cycle 23 was quite low and longer than we expected. And solar cycle 24 was a lot weaker than anything we had really seen for the past 100 years. And then it dipped down again to a much, so these are the predictions here, and so you can notice that our minimum, this gap, is how good we did, how well we did with our predictions. Not very great. And so the solar dynamo still needs a lot of studying, but we're in this deep solar minimum, and we're starting to come back out of it. And we're predicting, so another weaker cycle for this one, this upcoming one. So there is an interrelationship between sunspots, flares, and solar activity. So we usually correlate solar activity with the number of sunspots, and the more sunspots, the closer you are to solar maximum. So this is solar cycle 23 in fuzzy, unfortunately, I'm sorry. You can see there's not a lot of features on the sun, and then as you wind up to solar maximum, you get a lot of sunspots. These are images from the chromosphere, so a little bit higher up in the atmosphere, a little bit hotter gas. You can see there are these bright, active regions above the sunspots. So at solar minimum, you get, inside the sun, you get kind of a dipolar magnetic field arrangement. So you have a north pole at the top, a south pole at the bottom. The magnetic field lines are fairly straight at the beginning of the cycle. The sun rotates differentially, and so the equator rotates once every 25.8 days, and the poles take about 30 days. And so if you're rotating faster at the equator than at the poles, you're going to slowly drag this magnetic field around, and you get this stronger toroidal magnetic field component that coils up. Meanwhile, the sun is also convecting, and so you're churning it up from the deep, and you're mixing up the layers, and you get these complex, convoluted magnetic fields that eventually become buoyant and break out of the solar surface into sunspots. One of them is going to have a northern polarity, one of them is going to have a southern polarity, and then as the flow of the plasma in the sun is churning about from the heat, it will wind these up, and eventually they'll reconnect, release energy into a flare, and release some of this coiled up magnetic field. So this is one of the first sunspots of solar cycle 25. There's a little baby one that didn't do much about a month ago. But this one flared. So this is active region 2,750. So this is it in white light. So you can just see little traces of a positive polarity and a negative polarity of the sunspot. And so I only know the polarities because it's written down here. You can't see them from the white light. So this here is a magnetogram from SDO. I think it's from the HMI instrument. And so if this is in the northern hemisphere, the polarities would be opposite in the southern hemisphere of the sun. And the leading edge would be opposite for any sunspot affiliated with solar cycle 24. And so the polarity of this leading edge is how we can tell which sunspots belong to which solar cycle. And so this one flared, not very strongly, and so we're probably not going to get any hint of it at Earth, but it's still an active sunspot for solar cycle 25. So the sun is starting to wake up, so maybe we'll see some aurora, some more active space weather in 3 or 4 years. One can hope. Okay, any questions about that? Yeah.
I thought that the solar scientists, after they studied number 24, it was so much like the one that came just before the Dalton minimum in the late 1700s. And I thought the consensus was that we could be going into another Dalton-type minimum, or even worse, a Maunder minimum. And
Yeah.
now they're predicting 25 is going to be even bigger than 24. So what's the thinking on that now?
I mean, from what I've seen, I don't do solar dynamo theory. From what I've seen, there's quite a bit of variation. And the Dalton minimum still had little cycles. They just didn't have the same amplitude. The other thing is that sunspot number is one way to quantify solar activity, but you can also do it with F10.7, which is a radio emission, which is also decreased at these solar minimums. And so I think the predictions are that the sun is going to be quiet for the next little bit, but there's still a lot of variation on that.
Bear in mind, during the Maunder minimum, they didn't have all the equipment
No.
today, so there's a lot of speculation there.
Oh,
so,
yeah.
right?
There's a question from the back somewhere? Yeah.
In a solar minimum, is the sun cooler or warmer? Or does it change?
It doesn't really change. So there is a little bit less UV flux because you're not getting the same flares of quite the same activity. And the F10.7, which is the radio, is also a little bit less. But when it comes to visible light, that emission is still the same. Yeah, Michelle?
I'm just curious about that graph. It seems like there's another harmonic that's really long and slow. It keeps increasing and then decreasing.
This one?
Yeah.
No,
Yeah.
no, follow the entire thing.
Yeah, that is a peak.
Follow the peaks.
Oh, yeah.
Yeah.
That's the cycle.
Is it? I don't know. It looked like there's another cycle on top.
Yeah.
Maybe it starts to grow eventually.
Yeah, there is, so this follows the dipolar moment quite well, and that's that 11-year cycle. There are some theories of it, like the octopole moment in the solar dynamo. And so usually the dipole moment is strongest at solar minimum and kind of like resets itself. One of the differences in solar cycle 24 is that the octopole moment was almost as strong as the dipole moment, which meant that the entire magnetic field in the solar wind was weaker by about 30%. And so that was something that was still difficult to explain, but there's a chance that there's kind of an interchange, a periodic interchange between those two.
So there's several types of moments going on with different,
Yeah, I mean, it's
different periods.
Yeah, I mean, it is a chaotic, turbulent system.
Yeah.
So as far as dynamos go, there's still a lot of modeling happening, but that was something that we noticed for the first time in solar cycle 24, that we didn't know about before. Okay. Okay, so our last story is bubbles, heated clouds, point to active pass for galactic center. And so I showed this image in a different color map last time I did one of these. So this is the meerkat image of the galactic center. And so this is the galactic plane in the radio. We can see some shells of supernovae, these rosettes, also in the radio. And then what I focused on last time were these narrow filaments that are really bright in the radio, which are very interesting. But what I'm going to draw your attention to this time are these large lobes, these large meerkat lobes. And so these radio bubbles were discovered by meerkat, and they extend vertically above and below the plane of the galaxy. So for full disclosure, the northern lobe had been discovered a while ago, but this is the first time that we noticed that there's a roughly symmetric lobe to the south. This really allows us to see that these magnetic filaments, which also were discovered a while ago, align with the walls of these bubbles. So Ian Haywood used a radio mosaic from the meerkat array, which is a radio telescope array in South Africa, to find a pair of outflows emanating from the galactic center. So the galactic center is around here. So Sagittarius A is tiny in there. And so the northern lobe was discovered in 1984, and the southern lobe is being appreciated for the first time now. So it's roughly bipolar. And so these are not the only lobes that we know about in our galaxy. There are also the Fermi bubbles, which, if we zoom out and we look at the galactic plane in optical light, this is an artist's conception. There are large bubbles detected by Fermi. So it's this giant dumbbell sticking above and below the galactic center. But these two bubbles and lobes have very different scales. And so the Fermi bubbles extend 50,000 light years from end to end, whereas the meerkat lobes only extend 1,400 light years, so they're much, much smaller. And so the current hypothesis is that both sets of lobes and bubbles were actually emitted at the same time, but were emitted by different processes that had very different energies. And so that allowed the Fermi bubbles to expand out very rapidly, and the meerkat lobes to kind of just puff out weakly in comparison.
Daniel,
Yes?
what do those bubbles consist of?
Oh. I think they are hydrogen. Michelle, do you know?
Oh, it's
It's gotta be hydrogen gas.
Yeah.
I think it's hydrogen gas, and it's very hot.
Different temperatures, but it's in the radio.
Yeah. Hydrogen gas has been expelled.
Okay.
That's not a great answer. I'm really sorry. Okay. All right. So research currently estimates that this event that launched both the bubbles and the lobes happened a few million years ago. And so the Fermi bubbles and the meerkat lobes have similar ages, inflated by an outburst from the black hole, so that our galactic nucleus was more active. Yeah, okay, I've already said most of this. Okay, so some of the supporting evidence, or some of the interesting features, is that the smaller lobes appear to line up with the filaments. So this is a grayscale image of the meerkat. So you can see these narrow filaments in the radio, and so the edges of the meerkat lobes line up quite well with the filaments. And so likely what's happened is that you have electrons that have been accelerated that are now tied to the magnetic field, and as they orbit the magnetic field, they're emitting in the radio, and the bubbles or the lobes can be pushing out and compressing the filaments together, and so they could be lighting them up. Okay, so another piece of evidence, so there are the lobes and the bubbles that suggest that our black hole had a flare-up a few million years ago. There's another paper that came out recently out of Australia that supports this theory and also supports the timeline. And so this one, instead of looking at outbursts from, or potential outbursts from the black hole, looks at the Magellanic Stream, which is gas that's left behind by the collision of the Milky Way with the large and small Magellanic Clouds. And so they swept through our galaxy. The interaction ripped out some hydrogen gas and gas of different elements. And so you can see that there's this stream of gas that's most prominent in the southern hemisphere. There's a little bit in the north, but that's left over. So this is a stretched out map of the whole sky. And so you can see our galaxy, some dust in the galactic disk. And so here we're looking south at the Magellanic Stream. And so we've seen this in hydrogen. And so what this paper did is that they looked at different elements. And they found that they also saw thermal emission. But something, if it's still hot, something must have heated it up. Okay, so here, this is our black hole. These are two molecular clouds, which we can ignore for now. These in red are the filaments. And so these researchers added ultraviolet measurements of silicon and oxygen to their analysis. And so they had the hydrogen for meerkat and then also for this Magellanic Stream. And they found that the ions are in the same part of the stream as the hydrogen, and it traces out a large segment. And you can also see hints of the ionization, this is cut off, that appear in the northern patches. And so it appears to lie in a wide hourglass. And so you're seeing different ions, both north and south, that are glowing warmly. And so that's a little bit curious. And so the hydrogen clouds and the silicon clouds and the oxygen clouds are all cool. They cool at different rates. And so here I have a graph of, oh boy, okay, this is the galactic plane. This is the distance. And so here we have essentially a heating rate, or ionizing photon flux. Okay, this is from a model. Sorry, I'm going to come back to this. So what they've noticed is they've noticed that there is hot gas other than hydrogen, made up of stuff other than hydrogen, that's hot, but it's not, the different gases have different temperatures. And so the hypothesis is that something heated them up a long time ago, and because they cool at different rates, if we say, okay, well, if they start at the same temperature and they cool at different rates and they're at different temperatures now, I can trace backwards to guess how hot or when they all got heated up at the same time. Does that make sense? So if you like microwave coffee, the cup gets hot and the coffee gets hot and they cool off at different rates. So if you had those curves, you could like trace backwards and say, I microwaved it 10 minutes ago. So they're essentially doing that with gas. And so here they modeled a heating rate and an ionization rate to say when these gases would have been heated up or how much they would have been heated up based on the distance from the black hole. And they found results that are consistent. And so a plausible explanation for the temperature patterns that they've discovered is that Sagittarius A had a dramatic flare-up about 3.5 million years ago, which is consistent with the timeline for the Fermi bubbles and the Meerkat lobes. It could have either been one very large event or a succession of smaller ones. Things that make black holes flare up are accretions of large clouds of gas and dust. And so the gas probably heated up and it launched some jets. And the hot gas was emitted ultraviolet radiation. So powerful that it ionized gas and heated gas up in the Magellanic streams. And that extended about 250,000 light years away. So there's still disagreement about the Fermi bubbles origins and the Meerkat lobe origins, but the timing of all these three things seems to hold together and are a good match for the black hole having some sort of spectrum. There's also a young cluster of stars near the black hole that's about the same age, and so some of that gas might have been disrupted and triggers massive star formation, so that could hold together. So that could hold together. So those things all kind of indicate some sort of massive accretion on the black hole a few million years ago and a big flare-up. Okay, so here are my sources in various sizes, and that's it. I'll take any questions for this last one.
Given this type of data that we're seeing for our own galaxy, I'm assuming that we're actively searching for flare-ups or anything that there would be black holes, let's say, in other galactic centers, which is now a common hypothesis. Has there been any other indications of past besides our galaxy? Like if they've seen, I know it'd be a little tougher to get the level of detail we can see from our galaxy because of the distance and stuff.
Yeah, I think it's quite common to see radio jets on active galactic nuclei. So there are different levels of activity in galaxies, but for galaxies that are known to be active, we see these jets and these bubbles. It gets harder to see things that are closer and closer to the galactic disk. But based on the kind of distribution of activities of galaxies, I think we think that it's reasonable that they flare up when they're active kind of sporadically. Yeah?
Just looking at your diagram, I'm not sure the earlier ones where you see the Fermi bubbles.
Yeah?
I'm not sure the image scale on that, and 3.5 million years ago, it seems like that's moving up rapidly into galactic. Any idea of the rate that's moving?
Well, okay. The Fermi bubbles are about 25,000 light years across.
Right.
So if we think that the event that launched them happened 3.5 million years ago,
Yeah.
I'm not going to do that math in my head, but yeah.
Okay.
Yeah.
Still fast, 1.3C or something like that.
Yeah.
1.4C.
My ability to do arithmetic in front of people.
So are they thinking that like some of the jets that like we see from some of the active galactic centers now are like the same kind of thing would have happened, let's say hypothetically, if you were in another galaxy looking at the Milky Way 3.5 million years ago, you'd see an active jet coming off of ours kind of thing? And then,
I think so.
yeah,
I think so. Michelle?
not a continuous one, but like just a...
Yeah, my understanding is that these things kind of, a gas falls in and they flare up and they jet, and then it kind of, the infall stops, and then it kind of calms down, and you're left with these
Yeah,
kind
the
of random
jets
structures.
tend to be relativistic speed, the brains are probably not relativistic speed.
Right.
So they bump into interstellar-medium, which is gas, and it causes it to go and radiation. Yeah. The jets are typically relativistic, the gas, not so much. And wherever you get shock front, you get stellar formation. That's not really.
Yeah.
Any evidence of previous Fermi bubble-like objects around the galaxy?
That is a good question. I don't know. Michelle, do you know if they're like,
I would highly doubt it on the time scales that the things are happening. That's it there. It'd be cool to see the jets coming up.
okay, all right, any more questions?
All right, we're going to take a short break. We have some refreshments and treats. Courtesy of Gail and me, Kevin. All right. Mike?
One, two, three, everybody okay with that? Okay, well, before we begin, I've got some props to pass out here. If you could start at this level here, take one Pringle each, and then when you get to the back, come down the other side, and I'll start this one on the centre part here. One Pringle each. So you'll see why that's there later on. Well, here we are again. Thank you again. And we're going to talk about Big Bang Theory today, and I will explain what that really means, Big Bang cosmology, once we get going. Okay, there it is, the Big Bang. And here's our presentation outline. We're going to talk about some basic physics first, so that you can understand what I'm talking about with the universe. We're going to set the boundaries, so we can say what kind of universes are possible and not possible. Then we're going to look at the historical perspective. How did the Big Bang theory come to be? What led up to it? It's really interesting history which happened in the earlier part of the century, and you'd be quite surprised what people were finding out what it meant. So after that, we're going to talk about the expansion properties, as we know today, what we believe the properties are today. And then we're going to talk about the problems with Big Bang theory. We'll talk about the discovery of the cosmic microwave background and what the implications were of that. We're just going to touch upon one alternative. And then we're going to finish up the presentation with a thought experiment when we're going to be asking some very, very simple questions, and we'll see what kind of conclusions we can come up with then. So, basic physics, electromagnetic spectrum. I'm not going to spend too much time on it because I know time is limited. But what I wanted to point out, here's the visible part of the spectrum here. Here's the microwave part of the spectrum. So, the cosmic microwave background is in this part of the spectrum, which means when the light was released, when the universe first became transparent about 380,000 years ago, there was a hot fireball in the red-orange part of the spectrum, and the wavelength of the red-orange light has now been stretched this much into the microwave section, thanks to the expansion of the universe. So, some universal facts. The universe is incredibly huge, and all observations, latest observations, seem to indicate that it really is infinite. And as we see later, it's a lot easier dealing with an infinite universe than a finite one. So the speed of light incredibly fast, as we all know. It's often very difficult to sort of appreciate distance with that. Now, when we're looking into the past, as you know, when we look further and further distant, light takes time to get to us, so we're looking at the past. This is just basic cosmology. I think we're all aware of that. And the microwave background that we see was released about 13.82 billion years ago. But because of the expansion of the universe, what we are seeing now in the microwave background is actually now about 46 billion light years away because of the expansion of the universe, but we're just seeing the light that was released when it was a lot closer. Okay, we already mentioned that. And we mentioned that. Now, this is a question, is the vacuum, the true vacuum of space, really empty? Oops, where is it? No, it's filled with radiation. If radiation couldn't travel through space, you wouldn't be able to see the sun or the stars. So to say, because of Einstein, energy and mass are different forms of the same thing. So to say that the vacuum of space is empty, I'm not talking about quantum fluctuations coming in and out of the particles of space. I'm not interested in that right now. But the universe is filled with radiation. Don't ever think of it as a total vacuum at all. Otherwise, I'd say we wouldn't be able to see anything, would we? Okay, Ober's paradox. Heinrich Ober over there. How many people are familiar with Ober's paradox before I need to explain it? Maybe I should explain a little bit. Okay, what it says is that we all know about the inverse square law. If you double your distance from a light source, you get a quarter of the strength of the light. But when you double the distance, if you can imagine a sphere with that same radius, the radius of that sphere is a 4. Oh, geez. Boy. Sorry about this. Okay, what I tried to point out was this 4 pi r squared is the area of that circle. So what's happening is that as you go further away from the light source, you get more and more stars because if you imagine the universe being like a bunch of onion shell rings, and you look at the amount of light coming from each one of those spherical rings or spheres around you, the amount of light coming from each of those spheres, if you like, or edges of spheres, is the same no matter how far you are away. Because the inverse square law weakens the radiation by the square, but the area, the number of stars on that shell, are now squared as well. So basically, you get the same amount of light coming from each shell. So right away, that puts a limitation on the kind of universe, because years and centuries ago, people said, well, gee whiz, you know, I mean, this doesn't make sense, because everyone thought the universe was infinite, unchanging, stars shine forever. So, but we can see from this, it just doesn't work, because if you've got the same amount of light coming from each shell in an infinite, unchanging universe through time, then we're all going to burn up. So obviously, something else is going on. Oops. Okay, so solving it, let's have a look at the solution here. Infinite and uniform universe through time and space means you have a dazzlingly bright universe at night. And you know, the first person who actually came up with a sensible solution to this was Edgar Allan Poe. He said maybe those distant stars, the light hasn't had a chance to reach us yet since they were formed. And it kind of makes sense, eh? Because we all think the universe has been going on forever, but we know from the cosmic microwave background that we can only see so far back. So with that thought in mind, stars do not shine forever. And eventually all the galaxies are going to run out of energy to produce more stars anyway. And it's not infinitely, may not be infinitely old. And we can only see that far into the past. And because the space is expanding, that weakens the energy of the radiation coming to Earth as well. So the fact that we do have only a limit of how far we can see, and we've got the weakening effect because of the expansion, you know, no wonder the sky is dark. Makes sense. Now, what kind of limitations does this put on the type of universe? Could we have an infinite universe that's static? When I say static, it means it's unchanging through space and time, eh? Well, obviously not. Well, we'll look at that in a minute. Could it be infinitely expanding, finite and static, or finite and expanding? Those are the 4 basic types of universe we can have that takes no notice of whether the space might be curved. This is just basically. Well, Opal's paradox cancels out that option. This one appears to be the most likely. Could it be finite and static? Well, wouldn't gravity just take over and collapse everything? So that's not a good option either. And could it be finite and expanding? It's possible, but only if the universe is like a closed surface edge, just like the surface of Earth is like, appears to be infinite. When you go walking, there's no edge, there's no center. So if you imagine the three-dimensional universe on the surface of a four-dimensional sphere, then maybe something like this might be possible. There might be a limited number of stars, but you have to have curved space to do that. And right now, that doesn't appear to be the case. A little bit about cones here. I'll just write things up a little bit. Mathematical definition of a cone. You take an infinitely long line and you rotate it. And what you do is you scribe out a cone there. Now, if you intersect, like if that top of the cone there is precisely in the middle and the base is kind of flat, and you cut this thing parallel to the base, you'll end up with a circle. If you cut it at an angle, you'll end up with an ellipse. If you cut it so that it's parallel to one of the lines, you end up with a parabola. And if your intersection cuts both of the cone halves, then you end up with a hyperbola. And you might wonder, well, why am I talking about this? Well, there actually is a reason for this. There's three basic types of space that we could have. If we have flat Euclidean space, when all the angles in a triangle add up to 180 degrees, then we say we have zero curvature. And that's the way it appears from our observations at the moment. Now, if we're talking about a positive surface, when Gulliver came back from the land of giants, he brought me a nice big tennis ball. And if we imagine this is the Earth, start from the North Pole, go down to the equator, go west by 90 degrees, back north to the North Pole, we've got a triangle there with three right angles in it, which is 270 degrees. And on any curved surface where it's what we call positive curvature, that's what's going to happen to the triangles. They're going to have more than 180 degrees. Now then, if we think of negative curvature, that's a little bit difficult to understand. Now, if you look at your Pringle, you'll notice that it's shaped curved this way one way, and curved this way the other way, just like a saddle on a riding horse, eh? And that's the definition of negative curvature. And the reason I gave you a Pringle, because if you can imagine a straight line connecting triangles on your Pringle, you will find that the angles of the triangle, oops, oh jeez. Oh, I hate this. Why does it do this to me? Okay. Here's an example. It's not a very good example, but this is why I wanted to give you the Pringle, so you can appreciate yourself that when you've got two curvatures in opposite directions at right angles to each other, you've got negative curvature, and this is what happens to the triangles. And zero curvature would correspond to a universe that's where everything is perfectly balanced, the amount of energy that came from the beginning is perfectly matched by the energy lost through expansion. And that's an incredibly difficult concept to understand. But a flat universe, you could actually have a universe, it could be created in principle from zero energy, so you don't violate the conservation of energy. But it's very difficult to understand this loss of energy through expansion. And the only way I can really explain it so it's easy to understand, you remember when we were young, we used to have bicycle pumps? You know, you pump your tire up and it start getting hot because you're putting energy into that air as you're compressing it. Then if you let the bicycle tire cool down, undo the valve, the air feels cold when it comes out. Because as you expand anything, it loses energy. So, if the universe is expanding really fast at the beginning, which it appeared to be about the speed of light, it's losing a humongous amount of energy. And if the universe is flat, which means there's just enough mass there to keep the expansion going just forever in a parabolic fashion, then you can say everything's in balance, because the amount of energy from radiation and matter is perfectly balanced by the expansion, the energy lost through expansion. You kind of got to think of the negative energy this way. It's a very hard concept, but this is why I give you the bicycle pump, because hopefully it makes a little bit more sense now. So a lot of the cosmologists, they're absolutely praying and praying that the critical density, which will give you, critical density of the universe, which will give you just give you expansion forever, it'll be perfectly balanced by all the mass that's created as a result of that expansion. Pretty far-fetched, but that's the way the theory goes. Okay, now, this is a brief history. In the early part of the 20th century, everyone believed that our galaxy was the universe. Sure, the people in telescopes, they were spotting nebulae, but they weren't able to resolve any spiral arms yet. So everyone thought that the nebulae, which were distant galaxies, were actually all part of our own galaxy. It was 1917 that Einstein proposed his cosmological constant, because he believed that everybody else said the galaxy is the universe, and it's not collapsing, as far as we knew. So there must be something, other force, which is stopping gravity collapse the galaxy. So that's why he invented the cosmological constant. Now, Hubble's law of universal expansion was formalized in 1929, but around about 1925 we were already seeing spiral arms in some of those distant nebulae, and it was already proposed that maybe there's other island universes out there, just like our own galaxy. But the thing is, with our own local group of galaxies, because of the motions in that, some of them are blue shifted, like Andromeda Galaxy, which is moving towards us. So it was only later when Hubble was able to discover the more distant galaxies, that's when he realized that overall, in the big scheme of things, the farther the galaxies are away, the faster away they're moving for us. And that's what started everybody thinking, well, if we wind the clock backwards, it must have all come from an infinitely dense point. Which, as Jerry had once said in the experts thing, that's, yeah, it doesn't make sense. Anyway, we know that it's expanding from something anyway. So George Gamow and Georges Lemaitre, the Belgian priest, came up with all kinds of Big Bang theories to explain this. And again, they were discussing, is the universe open or closed? If it's closed, it means there's more mass energy than expansion energy being lost. So the universe will expand and then gravity will collapse it back again. Open means it will go on forever, whether it's sort of just forever or very much forever. So they were discussing things back there. Fred Hoyle came up with his steady state theory in '48, which was a big contender, big competitor to the Big Bang theory. And it was only in 1965 when Panzas and Penzias and Wilson discovered the cosmic microwave background. And that had been theorized long before that. But finally, they were actually able to establish that there really is this faint glow where the universe first became visible, if you like, when the ionization, when things were able to fall into atoms. And then cosmic inflation came along with Alan Guth in 1979. In the late 80s, Stephen Hawking has popularized cosmology and got a lot of people interested in it. And then at the end of the century, these two teams of people here discovered that what they were searching for, everybody thought at that time there was some titanic explosion, everything's flying apart, gravity is slowing it down. They wanted to find out how much the expansion was slowing down. That doesn't mean to say it can't go on forever, but they expected it to be slowing down somewhat because of gravity. But what they discovered, it wasn't slowing down at all, it appeared to be speeding up, which means in more recent times we've got negative curvature in the universe. So some of the early developments, the entropy heat death concept, that's basically saying eventually the mass and energy of the universe has to run out. You know, gas clouds form stars, they burn out, shed the stuff, you get new stars form from that with heavy elements, etc., etc. But eventually we're going to run out. So that's what the heat death concept is all about. No reason to assume expansion whatsoever back then. Why would they? Euclidean space was assumed. That means triangles all add up to 80 degrees. Einstein's special relativity in 1905, that's when he talked about time dilation, when you're traveling closer to the speed of light. The clocks run at different speeds. His general relativity was all about treating gravity as a curvature of space due to mass rather than an actual physical force. And his equations, boy, I'll tell you, just amazing. They did look at alternate geometries as well. And of course, when the quantum revolution came along, we got Max, Niels, Werner, Erwin, Wolfgang, Paul, Murray, and Richard Feynman. They contributed phenomenally to the whole science of cosmology because they realized then that on a very small scale, the way things act on the ultra small scale could play a tremendous part in what was happening in the very early part of the universe. So just to give you an idea of what we're talking about in curvature of space, like here's a graphical depiction showing the Earth. It's kind of warping like this around the outside. This is like a three-dimensional space around here. But he's depicting it in 2 dimensions so you can see how it warps. And similar picture in 1919, during the eclipse of the sun, this star, which was known to be over here, because of the warping with the light ray coming through the sun, it appeared to be misplaced by a few seconds of arc. And that's what really cemented Einstein's general theory of relativity, where they found that the star was not where they expected it to be because of the warping of space. Now, the last time I showed this warping at another presentation, somebody asked me an interesting question. Supposing the stars are up above the sun and we're viewing it down underneath. I thought, oh, gee, good question. Yeah, well, I said, that's not really that physical, it's just a representation. So what I did, I found another slide there which explains things a little bit. And this one shows you how gravity kind of sucks in the fabric of space all around you. So it doesn't matter where the light is coming from, it'll still be warped in the same fashion as it goes past the gravitating body. Does that make it a little clearer now, that one? Okay, so early theories. Now, Einstein's field equations from his general relativity gave all kinds of solutions. A lot of scientists back then were looking at what kind of universes could be possible now that we know about general relativity. And as I said, it was 1917 when Einstein proposed that lambda, the cosmological constant, is about the same as gravity, and that's what was keeping everything apart. But it was kind of hard to understand because we feel gravity, we see things in the motion of gravity, but he felt he had to do that because he had no idea at that time the universe was expanding. And he also assumed that the universe was static. You know, the galaxy, the Milky Way was our universe, and he actually assumed it had positive curvature because I guess maybe he was expecting more mass than expansion. Well, they didn't know about expansion. Now, Willem de Sitter, he modeled the universe with virtually zero density, which in reality is what we've got. I mean, 99.999% of space is space. And what he came up with was it's possible to have an infinite universe with accelerated expansion. And this was back in 1917. So why was everybody so surprised when they discovered the universe really was accelerating? It was known back then that it could happen. And then Alexander Freeman there, he talked about the closed oscillating universe. In other words, more mass than negative expansion energy, so the universe is closed. It expands and contracts on itself. Critical is when we're just on the limit, or you've got open universes where you have like that parabolic type of, hyperbolic type of universe. And then Georges Lemaitre, in 27, he came up with, and I think this was partly from observation as well, but he was claiming that you'd expect deceleration in the earlier parts of the universe because the universe was so dense that gravity would overwhelm any cosmological constant. Then as things keep on moving apart, the strength of gravity between each thing appears to be weaker, so then the cosmological constant takes over and then things start accelerating. And this is very similar to the current model that we have today. And this is back in 1927. And here's the model. I won't go into this too much, but they looked at negative curvature models up top with different values of lambda. And here's Lemaitre's one down here. Doesn't this just look exactly the way it's described today with accelerated expansion? And this guy had it nailed. And in fact, Hubble's law was often called Hubble-Lemaitre law because they discovered this together. So it wasn't just Edwin Hubble there. So, what are the expansion properties that we think we know right now? Well, Lemaitre first estimated the redshift in 1927, and he came up with a Hubble constant really large, probably about 1 order of magnitude, 10 times 10 pi. But he didn't really have a lot of data to go by. And you see that kilometers per second per megaparsec, that means that 2 items that are a megaparsec away, which is about 3¼ light years, in 1 second can expand by whatever the Hubble constant is, which is somewhere around about 60 to 70 today. I believe it anyway. But, you know, it's pretty hard to visualize what those units really mean. So I stayed up one night to figure it out, and I figured that the local h, which is 73.5 kilometers per second, and the very distant h is about 67, because with accelerated expansion, you would expect the expansion rate to be faster than what it was in the distant past. And I can't understand why the cosmological community is up in arms. How come these numbers don't agree? Well, if the universe is accelerating, obviously the h is going to be varying over time. I don't know what the problem is there. I'm missing something. But anyway, I did figure it out for you. The local expansion rate is about 11¼ meters per year per angstrom unit, the distance from here to the sun. So that means, I mean, the surface of the sun is all, you know, chaotic and everything. So, but there is hope that maybe in 100 years or so we might even be able to establish whether or not dark energy is actually operating within the solar system. Because if we find that the Earth is gradually moving away by 11 meters a year, then that gives very good evidence for the fact that dark energy is pervasive throughout the universe and not just between galaxies. Anyway, I hope that number is makes a little more sense to you about how fast the universe is expanding, not very fast. Anyways, 1929 he established this law, and it was believed back then that the universe must have come from an initially hot, dense state. That's all they knew. They didn't know what happened before that. And now if you think of, as we mentioned earlier, like the universe being the surface of a 4-dimensional hypersphere, then you don't worry about a center and you don't worry about an edge because there is none. But you've got to think in 4 dimensions to do that. And they say that space itself is doing the stretching, and that's what produces the redshift. That makes sense. And when George Gamow, Ralph Alpha, and Robert Herman predicted a 5-degree background radiation temperature based on the helium to hydrogen ratio in the universe, they came up with 5 degrees. I thought, well, that was pretty damn good, because when Zayas and Wilson discovered it was about 2.725 degrees. So I thought that was pretty good. I mean, it might sound, twice as much, but you're looking at degrees Kelvin, you know, and they didn't know a heck of a lot about what to expect, but they knew that somewhere in that kind of temperature range, we expected to find microwaves with that kind of temperature, if you like, yeah? Now, expansion concept. I'm sure you've all seen this before. I've even got a balloon here to show you. Now, I've got stars on this balloon, and I've got an imaginary wave of light there. Now, watch what happens to them when we blow the balloon up. See how the stars move away from each other everywhere on this surface with no center? And the wavelength gets stretched. There's your redshift, eh? But we won't dwell on that because I'm sure you will know that anyway. Okay, and now this is a logarithmic scale showing our solar system in the center. And what it's showing is like where we are here, it's been grossly blown up here so we can see the solar system because it's a logarithmic scale. But if you collapse that part, we then become part of a spiral arm coming out of our galaxy here. And it looks weird simply because the logarithmic scale is really distorting things, eh? Now, if you imagine that we're on, let's say we're on this little galaxy here, far, far away, like Star Wars. If you did something similar to them, the solar system, if they have one there, would be shown the way it is there. But their view of the universe that they can see will be different from our view, because they can see further that way than we can. And this around the edge is like the cosmic microwave background being represented. But wherever you are in the universe, we would expect to see the same kind of thing. And that's what they mean by isotropic, and homogeneous means it's basically the same everywhere. Yeah, there's holes and walls and everything, but in the huge scale of things, the universe is basically the same, eh? So, now when we talk about Big Bang cosmology, what we're talking about is what happened after the first 10 to the 43 of a second, if the universe really did start at all. We say that because we think we understand the laws of nuclear physics all the way back to that point. Further back in time, we need new theory uniting general relativity and quantum mechanics. We just don't know what laws the universe was operating under. They call it an epoch. You know, it sounds like centuries, but it's only 10 to the minus 43 of a second. And that is when the inflationary period was supposed to have happened, when suddenly the universe blew up a million magnitudes or whatever. And I've read all kinds of different things. Some say the universe was smaller than an atom, and after inflation it was as big as a grapefruit. Oh, that means it must be finite then. Other people say it was as big as the galaxy. Well, if the universe is infinite, well, we'll get into that later. But what we're interested in is what happened. The Big Bang cosmology describes the universe. Oops. Oh dear. Okay, describes the universe from that point onwards, where we think we know, we understand the nuclear physics then. In the next epoch, up to 10 to the minus 32 of a second, temperature was really hot, but it was, you know, the bare naked ladies had it right in the Big Bang theory. They said the universe was in a hot, dense state. Well, that's exactly what they believe it was. It was in a hot, dense state of seething quarks and leptons, very hot. But by 10 to the minus 6 of a second, it was cool enough for the quarks to clump together to form protons and neutrons. And by 3 minutes, it was just, everything was an ionized plasma. It's like the whole universe was like one gigantic ball of plasma, a massive, massive megastar. And as we know from the sun, plasma, if it's thick enough, it's opaque. All the charged particles don't seem to let the light through. I guess they're captured by the photons themselves. So the universe was still opaque at that time, even though it was still pretty hot, 10 to the 8th of a degree. But then, after about 380,000 years, it became cool enough, around about 8 to 10,000 degrees, I think, that you could actually, atoms could actually form. It was cool enough that electrons could combine around the atoms to form, combine around nuclei to form the atoms that we know today. So that is basically Big Bang theory, and then after that point, all the stars and galaxies were formed much later than that day. Like we figure after that initial burst of light was released into the universe, not outside the universe, it's all inside the universe, it became transparent. But then it took about 400 million years, they figured, before stars started forming, and another about 1 billion years before galaxies were able to gather the stars together. But that's all the Big Bang theory describes, from the time that we understand the physics to what we think is going to happen with that. And this is a really nice depiction of it. Fortunately, it doesn't, like most websites, talk about the Big Bang in the beginning. The Big Bang is that Big Bang cosmology actually starts here. After this period of inflation here, where we know nothing about the laws of the universe, or if it came from some other dimension, we know nothing about that, eh? Then it's got the hot soup mix there, and then it's got the rapidly cooling, it allows the quarks to clump into that. And we've already talked about that. This should be 380,000 years, by the way, not 300,000 years. But, you know, that was about the temperature they figured at that time when the microwave background was released. There's bright orange, red light. Billion years, if cool enough, that's when things that, well, I don't agree with that, but I've read elsewhere, I think the first stars were supposed to be about 400 million. But whatever, during that time period, from here to here, stars formed, then galaxies formed, and then today, universe hasn't changed a lot, except more and more stars and galaxies are forming, and then when the big early stars blow up, they shed their heavier elements through the universe, they form new stars, and then eventually there's enough heavy elements there that rocks and planets can form. It didn't happen right away. Just a quick model of basic nuclear physics, for those who are interested. These are the 6 quarks here that make up the protons and neutrons. These are the leptons. We've got the tau, the muon, and the electron itself, and these are their equivalent neutrinos. These are the force bosons, which mediate the different forces. The photon mediates the electromagnetic force. These 2 bosons, now actually there's a W plus and a W negative here, and this one's a no charge boson. They're the ones that deal with the weak nuclear force, which we've actually mathematically been able to combine with the basic electromagnetic force, and they call it the electroweak theory. And then the gluon, this boson here controls the mediation between the protons and the quarks, say. Now that one's hard to understand mathematically because there's been so many different models and none of them seem to describe it perfectly what's going on. So we think we understand what happened there, but in order to establish that, we probably have to build a particle accelerator the size of the solar system, because that's how much energy is involved if you wanted to try and create electroweak strong force, if you like, where all those 3 forces get together. None of this says anything about gravity, because for all we know, gravity may not be a force at all. It may just be a distortion caused by mass. Okay. Anyway, here's another depiction. And again, you see this a lot online, and the way they're describing it, you've got to imagine the outside of this surface as being like a 3-dimensional universe on a 4-dimensional surface. But, here they go. I mean, they talk about, they say quantum fluctuations start the thing off, but really we don't have a clue. If a universe came from nothing and nothing is really nothing, where will the quantum effects, Anyway, they do mention inflation, that rapid period expansion. Then they've got the afterglow of the Big Bang. Now, at least here, you can see the Dark Ages, which I didn't really show too well on the last picture, because that was the gap from the time the microwave, before the cosmic microwave background traveled through transparent space, there was a long period of darkness before the first stars formed. And that's what they call the Dark Ages. And they got first stars about 40 million years, and then, but they don't mention when the first galaxies were formed. But so every picture you find has got some good things and some things missing in it, So that's why I had to sort of show a few of them. Now this one here, is this the current consensus? Well, they got the Big Bang at the very beginning, which they assumed was like some kind of mythical singularity, which really means nothing to anyone's brain at all. They do mention inflation, they mention the background, the Dark Ages, the first stars, first galaxies, so that part is right. But is this the current consensus about the Big Bang? No. Big Bang cosmology starts after inflation, when we think we understand the physics that was operating. That is all the Big Bang theory is about, what we understand. Now here's another picture I like. Once again, the outside surface of that trumpet, if you like, is the 3-dimensional universe which is being depicted. Now, it's got Big Bang inflation there, they just combine the two. They've got the Dark Ages, they've got the CM cosmic microwave background, geez, get out of here. Okay, they've got, they don't say much about when the stars and that were formed, but what I like about this picture, if you can imagine drawing a straight line from here to there, and back again, you'll find that it will dip down, so you get a triangle with all sides pushed in, so the angles of the triangle will be less than 180 degrees. And that appears to be what's happening now, because we believe from observation that the universe is accelerating in its expansion. So here's a picture from WMAP, the Wilkinson Microwave Anisotropic Probe. And that was how they showed the, I know it can't be Kobe, because Kobe was much coarser than that. You just had various blotches of blue and yellow, red on it. But when the WMAP probe went up, they got a really good picture of the Big Bang, a microwave background, I should say. And later, when the Planck satellite went up, we had an incredibly detailed picture there. And this is the picture that everyone is saying, oh, we can look at all the different moments and everything in that picture there and come to all kinds of conclusions. But I think there's a bit of a problem with that. Like, here is the large-scale structure of the universe. You've got all these filaments and dark holes where there appears to be almost nothing. And they modeled this on the computer too, so they believe, that this is how gravity would act in the long term. And also dark energy too. That's played a huge role too in the sculpting of the universe as well. And I'm so glad that Daniel talked about the lensing effect there, because here's a nice colored picture that shows all kinds of lensing examples. All these things here, all these things are basically where you've got gravitational lensing from objects which are behind some of these ones in the foreground. Now, in order for gravitational lensing to happen like that, the trajectory of the cosmic microwave background, it can't come to us on a straight line. It's being warped all the way according to the path it takes through the universe with the galaxies and stars. So if you look at this picture here, and you will rarely find this one in the literature anywhere, because nobody wants to talk about this. But if you've got 3 points here, oh gee, go back. Okay, let's get this right here. Maybe I should use this one instead. But if you follow the trajectory from 3 points from that microwave background, where we view them from probably bears no relationship to their actual position at all. So all of these conclusions they're coming to about the cosmic microwave background and all the kind of different inflation models and everything, I don't know if they've got it modeled right. I mean, really. I mean, the universe is full of things which are going to bend that light. So really, what kind of conclusions can we form? I doubt very much that some of the conclusions are valid about the cosmic microwave background, simply because of that picture. And we got some problems. Now, this ultimate free lunch, which Alan Guth talks about, is saying that, in principle, you can get a universe from nothing if the negative expansion energy balances the positive mass energy. If they're exactly balanced, then you can, in theory, if we knew how, create a universe from nothing. Bit iffy, bit hard to understand, no indication how that could be done, but yeah, and this thing too, about the universe from an infinitely small point, I kind of poo-hooed that a bit, but I'll see at the end of the slide, you'll see a much better solution. Where was the center of the explosion, or where's the edge of the universe now? Well, if you understand this concept of a 4D universe on a hypersphere of light, then those problems disappear. I won't talk any much about the anthropic laws, but all that means is that all the basic constants of nature, they're so incredibly finely tuned, if any of them were slightly different, stars couldn't form, things wouldn't form, and we wouldn't be here. So it almost appears like the universe was made for us. And that's why a lot of the spiritual people say, well, this is the proof that God exists. The Pope has said that. But this side of the subject is much better talked about in another presentation. I've got presentations about the stuff around this and what really happened near the beginning and the possible options. And that's where the whole idea of the multiverse came from. But that's the subject of another talk completely. But I've just mentioned that because that does appear to be a problem. Why is everything so finely tuned for us? And again, the physical laws are unknown prior to that magic 10 to the minus 4 to the 3 because quantum effects come into play before that, earlier than that, and who knows what role they play. Now here's a problem too about matter versus antimatter. Nobody can really get a handle on why is the universe almost exclusively matter, what happened to the antimatter? Did it blow off in another universe or away from it? I mean, who knows? But it is a problem that hasn't really been addressed yet. How did the universe begin and why? And these are modern questions that people are asking now because nobody dared ask those questions a few decades ago. In other words, what caused the Big Bang to bang? And that's one of Alan Guth's famous statements right there. He says, what bang, why did it bang, and what was happening before the Big Bang? And we don't know anything about that. And none of this is anything to do with Big Bang cosmology. I wanted to mention it's happening, but there are more problems. Why is the cosmic microwave background so smooth? Well, we found out now that it's not really that smooth, but it's, with a rapid expansion, you have to ask the question, well, how can one thing communicate with another when there's no time to get there? Why does everything appear to be so equal everywhere? Well, we don't really understand the initial conditions. So, if there was any initial conditions. Now, the horizon problem is something that's solved. Now, that again, that's a very similar problem. Why is everything look so the same? And inflationary theory tends to solve that problem, because by expanding the universe really fast, if it really is a finite universe, if you expand it so that the radius of that hypersphere is like 10 to the 100th to the 100th trillion light years, or something huge like that, then of course it will appear to be flat right now. Okay, that's, yeah, flatness problem. We've already talked about that zero energy problem I was talking about. Did I make that clear? It's a hard concept to grasp, isn't it? Positive energy balancing negative energy from expansion. So I hope I got that across, because that is not an easy concept at all. Now, in the early universe, it's believed that all the forces were one, and as they split apart, as the electromagnetic force split off from the electroweak force, it should have created a whole bunch of magnetic monopoles which have never been observed. Now again, Alan Guth explains that with rapid inflation, that problem tends to disappear, but I'm not so sure about that. In other words, now, you see this omega here. Now, when omega is 1, it means that the critical density is exactly the same as the real density in the universe, and we are expanding parabolically, which we know we're not now because we've got accelerated expansion. But if omega is not equal 1 and you have an imbalance, there's more mass energy than expansion energy, then where did all that energy come from in the first place to create such a massive universe? So that's an issue, unless it's infinite. Okay, and here's another thing which has come out quite recently in observations. The cosmologists are now finding evidence for supermassive black holes way back when the first stars were forming. Not a billion years after the expansion, but way before that. And nobody can understand how they could have possibly formed in the time available. So that is an issue. Did they come in from another universe? Is it a white hole that they think is a black hole? The jury's out on that, but it is a problem as far as the Big Bang theory. Well, actually, all this is beyond the Big Bang. This is not really... and then say, well, what about gravitational lensing? That's another issue. And I think that one should be in the literature more, because I don't think anyone's ever thought about it seems. Okay, modern developments, grand unified theories, theories that hope to unite the electroweak source force with the strong nuclear force, theories of everything, theories that hope to unite gravity in the equation as well. Scientists have been working on that since the 70s. Then string theories and M theory. Now, M theory is just a collection of all the different string theories. That started in the early 80s. Now, this is the one, I don't know how, but they say that the observations of the cosmic microwave background indicate that the universe is indeed infinite and edgeless. I agree with that statement, but I don't know how you can start here, draw a triangle to the cosmic microwave background over there, draw another arm of the triangle to the cosmic microwave background down over there, knowing that the whole surface is curved anyway around us. How they're ever able to seduce that the angles of a flat triangle add up to 180, I don't know. But somehow they do seem to have evidence that this is true, and I believe that's true, but I just don't really understand the math behind it, you know. Okay, it wasn't until 98 when the accelerated expansion discovered, we hit that. And this basically turned cosmology totally upside down, because it caught them all by surprise, it's funny enough, even though back in the early 1900s, it was known that this was a distinct possibility, mathematically, that it could happen. And 20 years later, we don't really understand what dark energy is. But again, that's the subject of another talk, because this is beyond the Big Bang cosmology can't explain any of that. As I said, all we're just talking about is what we understand from the hot dense state onwards. And I call the 21st century the age of imagination, because you wouldn't believe the wild ideas that are coming out to explain the universe. And again, subject of another talk. So I just want to introduce you briefly to this cyclical oscillator, which was proposed many, many decades ago. Then it kind of fell from favour, but now it's become a little bit more popular. Like what this would be like each period of expansion and contraction. This is like our universe will be, say, like up here somewhere. But the theory goes, and I'll explain it on the next slide, that when it eventually collapses here into a very, very dense, we'll call it a point for now, but if you look at this one, I don't know if you've heard of quantum loop gravity, but the scientists are working on that. They have come to the conclusion that in extreme conditions, things could actually do a flip and turn inside out. And that could help explain the bounce, if you like, from one universe to another after it collapses. And I remember the CPT theorem from the 60s and 70s. If you change the charge, like if all matter became antimatter, was reflected in a mirror, and run backwards in time, you would be able to tell the difference from the original. That's how weird quantum mechanics is. So they're using all of the theory, what they believe happens in quantum mechanics, to say that it might just be possible. You know? So here's an explanation. They say about a 10 to the 100th years from now, as we said before, eventually we're going to run out of energy, eventually. And this may cause the dark energy to turn negative, and the universe might start collapsing because there's no positive energy to keep it out there. So if it goes back to the hot dense state, and quantum mechanics forbids anything getting too close, so this whole idea of an infinitely small point is just fiction. But what they say is that the laws of physics break down after 10 to the minus 43 per second, but maybe before that, maybe quantum loop gravity could actually make everything become negative, and it could turn the big crunch into a big bang. I mean, pretty iffy, but at least it gives some kind of an explanation of where it may have all come from. But again, that is beyond Big Bang cosmology. But at least it gives you some idea that scientists are thinking about how it may have happened. Oh, we're not doing too bad. Okay, just a couple of slides. Now, I want to do a little thought experiment with you folks. No difficult questions, I promise you that. Okay, let's assume that the universe really is infinite. And infinite means there is no edge, it goes on forever and ever and ever and ever. There is no edge, just like if you try walking around the world, if you don't know where the beginning is, you'll walk forever. Same kind of thing, you know. So if the universe is infinite and flat, say, it really is truly infinite, the amount of stuff there. Let's try and wind the clock back and see what happens if we go back in time. All the way back to the so-called beginning. Well, let's say, I don't know, maybe about 7 billion years ago, galaxies are, let's say, only half as far apart as they are now. So the question I have for you is, how big is the universe now?
Infinite.
Thank you. Right. Okay. Eventually, if we keep on going like that, if all the space gets shrunk up by negative dark energy, it just disappears from existence and all the stars are touching, how big is the universe now? If it starts off infinite, the instant you put a boundary around the universe, it was never infinite to begin with. So, okay, so we've still got an infinite mass of stars together. Now all the atomic nuclei are touching, like a negative neutron star, and then the quarks are touching, and we're at the point now when quantum mechanics can't allow anything to get any closer together. How big is the universe now?
Infinite.
It's infinite. Thank you. So at what point does the universe become finite? It never does. So maybe the universe began from an infinitely large point instead of an infinitely small point. Doesn't that make a lot more sense? It does to me. I hope it does to you. And you'd be surprised at the number of problems that go away when you think about this. Okay. If the universe is finite and it all collapses under gravity, you're going to have such an incredible gravitational field. It's going to be immense. But if you're in the middle of a quark star, which is infinitely big in size, you're going to have gravitational forces reasonably equal around you. You know, I mean, maybe there's variations, but at least it won't be an infinite gravitational field because it's pulling you in all directions from the infinite universe. There's no need to describe the universe as a 3D surface on a 4-dimensional hemisphere now. You don't need that anymore because you can explain it by thinking that coming from the infinitely large point. Quantum mechanics will still function as it does now. Think of negative energy shrinking space instead of expanding it. And I often wondered if anyone's really looked at the what happens when photons meet. I mean, when we shine the flashlight on the wall, there's a very, very, very minor force that hits the wall, the photons. But when you've got the universe full of radiation, which is why I mentioned that early on, there's all kinds of photons all around the universe. You know, could the energy from that, when they intersect, could they actually create space and expand space? So if we totally run out of energy, there's nothing more to create that expansion, and everything might just start collapsing again. Anyway, it's all speculation. Anything beyond Big Bang theory is mostly speculation anyway. You know, but as I said from last night, if space does shrink to nothing, there's no more space there. If you've only got a sea of touching quarks, then maybe quantum low gravity, if it's real, and they can never find a proof for that, or very, very positive suggestion that's the case, then maybe they will actually come up. Because if they can ever unite the forces properly, then it might explain how this all happened. It might even explain why the constants are the way they are. We just don't know. So, basically, that's what I have. So, go wild. It's your turn. Yes?
If the universe, pre-universe, Big Bang started as an infinitely small point,
That is what the consensus says.
but wouldn't that explain the uniformity of the cosmic background radiation? Because an infinitely small
Yeah,
point
but when
would
does the
allow
infinitely small
radiation.
point become an infinite universe?
I don't know. But I'm saying if it
That's
starts
why I
as-
had to do the thought experiment.
Yeah, but if it
If you
starts
think
as-
of an infinitely large point, it's so easy to understand. Like if you're inside that fireball at the beginning, there's no question of this microwave background escaping out because the whole universe is you're in it. It's all around you everywhere, infinitely. And at the time, 380,000 years of expansion, suddenly the universe is transparent and you're in it. So it's much easier to understand that as well if you look at it this way. So, yes?
Yeah, I saw YouTube with Alan Guth.
Alan Guth, yeah?
Yeah, he's a father of inflation, and he was saying that the moment there are no monopoles, because at the time that the universe was in equilibrium and began to expand at 10 minus 35 seconds, it was at 10 to 28 degrees, which is where it always happens. And when that happens, at the time of the inflation, everywhere in the universe, it wasn't just one place that inflated, it was a number of them.
Yeah, exactly, but it's very rarely described that way in the literature.
And every time.
That it was everywhere in the universe. eh?
But all those locations, at the beginning of all those universes, were they were too small to allow the passage of a monopole. Just one monopole would make it, not more than one. They did their calculations.
Yeah, I know he did come up with an explanation. He said that inflation would solve that problem. I just wasn't sure completely how, though.
And there was one other thing too, and that was that with respect to what is it?
catch you later. There might be somebody else asking the question. Anybody else got something? Okay.
Is it possible that James Webb Space Telescope will be able to see further than 13.8 billion?
I can't wait for that telescope to get up, and I hope they don't have the spherical aberration problem again with the lens, with the mirror. Yes, that's what they're hoping. It's an infrared telescope because they're hoping to find early stars in the universe, or maybe just early stars, where they're redshifted into the infrared. That's why it's an infrared telescope. And it's got so much more light gathering capacity than the Hubble that yes, it should open up a whole new chapter of cosmology, and I can't wait to see that. I just hope they do it this time, you know. Okay, Jay, you had a problem? Question? Yes, sir.
So, you mentioned there was a model you showed the universe expanding and contracting and
Yeah, the cycling
expanding.
model, yeah.
What's the status of that? In
It's-
terms of,
It's become more popular in the last 20, 30 years as a possibility that it might be real. It was popular early, then it fell from favour, but now with this quantum loop gravity work that's going on, now they're looking at it as a real possibility maybe.
okay, so if that's the case, unless the laws of physics change in those contraction periods, isn't entropy still a problem?
That's what I thought of, but when people ask me that, I think, well, if the CPT theorem, when you've got antimatter in a mirror image going backwards in time, being indistinguishable, maybe entropy is the same part of that as well. Maybe it's indistinguishable. I mean, because normally, as you say, when things are becoming more ordered, entropy is decreasing, which is what it would be under a collapsing universe, because when everything is all touching, it can't be any more ordered than that. So then maybe as it expands, then entropy starts increasing again, the randomness. I know it's a difficult thing there, because I know I've done thermodynamics to do, and that's one of the biggest problems about this. But I'm sure with the loop that will all be taken, it will all be explained once they get it properly formulated, I hope. Anyway. So anybody else before we go back over here? Yes.
Worth pointing out that the universe is 13.7 billion years old, but its size is not 13.7 billion light years.
Well, I mentioned that, like right now it's about
The size
40.
of the universe back to 13.7 billion years is 42.3 billion light years. And so the whole size of the observable universe is just under 100 billion light years, 93. Now, statistical analysis on the parameters of the universe has indicated that the absolute minimum size of the universe is 251 times larger than that.
Yeah.
It makes minimum size of the universe is 2.5 times 10 to the 13 light years.
Yeah, it's pretty
So
big.
people who talk about things being 13 light years or billion light years away, no, they're 40.
No, I didn't say that. I just said it was released that many years ago. I mentioned in there that right now it's about 46 billion years that it's expanded to. It's just time I was talking about. I was saying time-wise, 13.82 like years, whatever it is, billion years ago. Okay, have you got your question ready now?
I just wanted to point out that
Speak up.
just want to point out that
Can you see me afterwards? I can barely hear you, and I think we've got to end the meeting now.
okay,
See me afterwards. Okay? Got to get out of here.
Yeah, thanks, Vic.
Sorry, I'm trying to lean out.
You got some magazines, you guys want to help yourself to it. And I did call Boston Pizza, we're running a bit late, but thank you for everyone coming out.